You are listening to the Practical Linux Administrator, your hands-on guide to managing Linux systems reliable and efficiently. Like and subscribe to keep up to date on our latest audiobooks. The Practical Linux Administrator, your hands-on guide to managing Linux systems reliable and efficiently. Chapter 1, Welcome to the Linux World, the Administrator's Journey. 1.1 Introduction. Why Linux Matters. In the vast and ever-expanding universe of computing, an operating system is much like the conductor of an orchestra. It coordinates all the components, from the hardware humming inside your machine to the hundreds of software applications you interact with daily. While you might be familiar with operating systems like Windows or macOS on personal computers, there's another player that silently, yet fundamentally, powers the digital infrastructure of our planet: Linux. 1.1.1 The Pervasive Power of Linux. You might not see a Linux Inside sticker on every device, but its presence is truly everywhere. Think about it: the internet. A staggering majority of the world's web servers, the machines that deliver websites to your browser, run on Linux. When you access Google, Facebook, Amazon, or Netflix, you're interacting with vast arrays of Linux servers. Cloud computing. Giants like Amazon Web Services, AWS, Microsoft Azure, and Google Cloud Platform rely heavily on Linux to power their virtual machines and services. If you're building in the cloud, you're almost certainly using Linux. Smart devices. Your Android smartphone, tablet, or smart TV is built on the Linux kernel. Even many smart home devices and embedded systems utilize a version of Linux. Supercomputers. Every single one of the top 500 fastest supercomputers in the world runs on Linux. Its efficiency and scalability make it ideal for tackling complex scientific calculations. Data centers. From network routers to specialized storage devices, Linux is the operating system of choice for enterprises large and small, providing the backbone for their operations. This pervasive presence isn't accidental. It's a testament to Linux's unparalleled stability, security, flexibility, and the vibrant global community that drives its continuous improvement. 1.1.2 What is an operating system? Before we dive deeper into Linux, let's briefly clarify what an operating system, OS, is. Imagine your computer's hardware, the CPU, memory, storage devices, network cards, as the instruments in our orchestra. Without a conductor, they're just an inert collection. The operating system is that conductor. The OS performs several critical functions: resource management. It allocates the computer's resources, CPU time, memory, storage space, among various programs and users. Process management. It starts, stops, and schedules programs, called processes, to ensure they run efficiently without interfering with each other. Memory management. It keeps track of how memory is used and allocates it to applications as needed. File system management. It organizes and manages files and directories on your storage devices. Input-output handling. It manages how programs interact with input devices, keyboard, mouse, and output devices, monitor, printer. User interface. It provides a way for users to interact with the computer, whether through a graphical interface, like on Windows or macOS, or a command line interface. Linux excels at all these tasks, particularly in environments where stability, security, and the ability to run without a graphical interface are paramount. 1.2 A brief history of Linux. The story of Linux is one of innovation, collaboration, and a revolutionary idea: the power of open source. 1.2.1 From Unix to GNU, the foundations. To understand Linux, we first need to briefly look back at Unix. Developed in the late 1960s at Bell Labs, Unix was a groundbreaking operating system known for its modular design, portability, and powerful command line interface. Many of its core concepts and tools are still alive in Linux today. Over time, Unix evolved into various proprietary versions. In the early 1980s, driven by a desire for free, as in freedom, not necessarily zero-cost, software, Richard Stallman launched the GNU project. His vision was to create a complete, free, Unix-like operating system. By the early 1990s, the GNU project had developed many essential components: compilers, text editors, utilities, but it was missing one crucial piece: the kernel. The kernel is the core program of an operating system, the part that directly interacts with the hardware and manages resources. 1.2.2 Linus Torvalds and the Linux kernel. Enter Linus Torvalds, a Finnish computer science student. In 1991, frustrated by the limitations of the MINIX operating system, a small, educational Unix-like OS, he began working on his own kernel primarily as a hobby. He announced his project on a Usenet group, soliciting feedback. "I'm doing a free operating system, just a hobby, won't be big and professional like GNU for 386, 486 AT clones. This has been brewing since April and is starting to get ready. I'd like any feedback on things people dislike in Minix, as my OS resembles its somewhat same physical layout of the file system due to practical reasons." This humble beginning led to the creation of the Linux kernel. It wasn't long before programmers from around the world started contributing to Linus's hobby project. What made it special? Linus decided to release the kernel under the GNU General Public License, GPL, which essentially meant anyone could use, modify, and distribute it, provided they also made their changes openly available. The magic happened when the almost complete GNU system met the newly robust Linux kernel. Together, they formed a complete free operating system, GNU Linux. While often simply called Linux, it's important to acknowledge the vast contributions of the GNU project. 1.2.3 The Open Source Philosophy. The story of Linux is a shining example of the open source philosophy. At its heart, open source means transparency. The source code, the human-readable instructions that make up a program, is openly available for anyone to inspect. Collaboration. Developers worldwide can contribute, find bugs, and suggest improvements. Freedom. Users are free to run, study, modify, and distribute the software. This collaborative model has led to incredibly robust, secure, and rapidly evolving software. Instead of a single company dictating development, thousands of eyes scrutinize the code, leading to faster bug fixes and continuous innovation. This is a significant advantage, especially in the context of critical infrastructure like servers. 1.3 Why Linux for System Administration. Given the choice in operating systems, why does Linux often stand out as the preferred platform for system administrators, especially in server environments? 1.3.1 Stability and Reliability. Linux is legendary for its uptime. Servers running Linux can often operate for months or even years without needing a reboot. This is critical for services that need to be available 24/7, such as websites, databases, and enterprise applications. Its design is inherently robust, with resource management and fault tolerance built into its core. 1.3.2 Security and Auditing. While no system is impervious to attack, Linux has a compelling security story. Its open-source nature means vulnerabilities are often identified and patched quickly by the community. It boasts sophisticated permission systems and security modules, like SC Linux and AppArmor, that can confine applications and users, significantly reducing the attack surface. Furthermore, Linux's robust logging capabilities make it easier for administrators to audit system activity and detect potential intrusions. 1.3.3 Flexibility and Customization. This is perhaps where Linux truly shines. Because its source code is open, it can be endlessly customized to fit specific needs. Want a tiny operating system for an embedded device? Linux can do it. Need a powerful server for complex computations? Linux can be configured just so. You can choose exactly which components to install, often resulting in leaner, more efficient systems compared to monolithic proprietary counterparts. This flexibility is what gives rise to the hundreds of different Linux distributions we'll discuss shortly. 1.3.4 Cost Effectiveness. Most Linux distributions are free to download and use. This eliminates initial licensing costs, which can be substantial for large deployments of proprietary operating systems. While enterprises often pay for commercial support packages, like those offered by Red Hat, the underlying software remains free, significantly reducing the total cost of ownership. This makes Linux an attractive option for startups, nonprofits, and anyone operating on a budget. 1.3.5 Strong Community Support. Beyond commercial support, the Linux community is vast, active, and incredibly helpful. If you encounter a problem, chances are someone else has faced it before, and a solution can be found in forums, wikis, or mailing lists. This collective knowledge base is an invaluable resource for administrators at all levels. 1.3.6 Cloud Dominance. Today, the vast majority of virtual servers in public cloud environments, Oz, Azure, Google Cloud, run on Linux. If you plan to work in cloud infrastructure, mastering Linux is not just an advantage, it's a fundamental requirement. Your ability to navigate a Linux command line directly translates to managing powerful server instances remotely. 1.4 Understanding Linux distributions. You've probably heard names like Ubuntu, Fedora, Debian, or CentOS. These are all Linux distributions. But what exactly does that mean? 1.4.1 The kernel and user space distinction. Think back to our orchestra analogy. The Linux kernel is the conductor, the core program that manages the fundamental operations of the hardware. However, a kernel alone isn't a complete operating system. For a system to be usable, it needs a suite of applications, utilities, and tools. This collection of software layered on top of the kernel is often referred to as the user space. A Linux distribution is essentially the Linux kernel bundled with a carefully selected set of user space software, configuration tools, and a package management system, all assembled by a specific organization or community. Each distribution makes different choices about which software to include, how often to update it, and what default configurations to use, tailoring the system for specific purposes, e.g., desktop use, server use, security testing. 1.4.2 Major distribution families. While there are hundreds of Linux distributions, most fall into a few major families, sharing common packaging and system management approaches. Debian family, Debian, known for its stability, vast software repositories, and commitment to free software. It's a foundational distribution from which many others derive. Ubuntu, a very popular and user-friendly distribution based on Debian. Ubuntu comes in desktop and server versions and is widely used in cloud environments. It aims for a balance of ease of use and administrative power. Mint, a popular desktop-oriented distribution based on Ubuntu, focusing on user experience. Red Hat family, Red Hat Enterprise Linux, RHEL, a commercial, enterprise-grade distribution renowned for its stability, long-term support, and extensive documentation. It's often used in large corporate environments. CentOS Stream, previously a free community-supported rebuild of RHEL, it is now an upstream development platform for RHEL. It's ideal for those who want to get closer to the cutting edge of RHEL development. Fedora, the community-driven, cutting-edge distribution sponsored by Red Hat. It's where new features are developed and tested before potentially being incorporated into RHEL. It's great for those who want the latest software. For learning system administration, focusing on one distribution from each of the major families, Ubuntu Server from Debian and CentOS Stream from Red Hat, can provide a broad understanding of common administrative practices. This book will highlight commonalities and note key differences where they exist. 1.4.3 Choosing the right distribution for learning. For new system administrators, Ubuntu Server or CentOS Stream are highly recommended starting points. Ubuntu Server is straightforward to install, has excellent documentation, and its package management system, often called apt, derived from Advanced Package Tool, is relatively intuitive. Its widespread use in cloud environments makes it a highly relevant choice. CentOS Stream gives you experience with the ecosystem that underpins Red Hat Enterprise Linux, which is prevalent in many corporate data centers. Its package manager, often called DNF or historically Yum, is also widely used. Throughout this book, we'll strive to provide examples that work across these distributions or clearly identify where commands might differ. 1.5 The role of a Linux system administrator. So, what does a Linux system administrator actually do? Essentially, they are the guardians and caretakers of Linux-based systems, ensuring they run smoothly, securely, and efficiently. 1.5.1 Core responsibilities. The tasks of a sysadmin can vary widely depending on the organization and its size, but common responsibilities include installation and configuration, setting up new Linux servers, physical or virtual, and configuring them to meet specific requirements, maintenance and updates, applying security patches, upgrading software, and performing routine system health checks, user and group management, creating, modifying, and deleting user accounts, managing permissions, and ensuring proper access control. Monitoring, keeping an eye on system performance, resource utilization, CPU, memory, disk, and identifying potential bottlenecks. Security management, implementing security best practices, setting up firewalls, and responding to security incidents. Troubleshooting, diagnosing and resolving system issues, from slowdowns and errors to outright failures. Backup and recovery, implementing strategies to protect data and restore systems in case of disaster. Automation, writing scripts to automate repetitive tasks, improving efficiency and reducing human error. Networking, configuring network interfaces, managing firewalls, and ensuring connectivity. 1.5.2 Essential Skills. Beyond technical knowledge, successful Linux system administrators possess a critical set of skills. Problem solving, the ability to methodically diagnose issues, research solutions, and apply fixes. This is arguably the most important skill. Command line proficiency. This cannot be overstated. While graphical tools exist, the command line is the most efficient, powerful, and often the only way to interact with server-side Linux environments. Scripting, especially Bash, automating tasks saves immense time and reduces errors. Basic shell scripting is a fundamental skill. Networking fundamentals, understanding IP addresses, ports, protocols, and how to configure network interfaces is crucial. Security awareness, a proactive mindset towards securing systems and understanding common threats. Attention to detail, small configuration errors can have big impacts. Patience and persistence. Troubleshooting can sometimes be a long and challenging process. Continuous learning. The technology landscape is always changing, requiring sysadmins to constantly update their knowledge. 1.6 Your learning journey ahead. This book is designed to provide you with a solid foundation in all these areas. It's a journey, and like any journey, it requires active participation. 1.6.1 Setting up your Linux lab. The best way to learn Linux system administration is by doing. You'll need a safe sandbox to experiment, make mistakes, and fix them without risking your main computer. The ideal solution is to use virtual machines, VMS, virtualization software, like Oracle VirtualBox or VMware Workstation Player, both free for personal use, allows you to install and run multiple operating systems as guests on your existing host computer. Think of it as having several separate, isolated computers running simultaneously within your single physical machine. We'll guide you through setting this up in the next chapter. 1.6.2 The importance of hands-on practice. Reading alone won't make you a Linux administrator. You must actively follow along with examples, complete the practical exercises, and even intentionally break things to learn how to fix them. The more you type commands, configure services, and troubleshoot problems, the deeper your understanding will become. 1.6.3 Embracing the Linux philosophy. Linux isn't just an operating system, it's a way of thinking. Embrace the open source spirit, the power of the command line, and the vast resources of its global community. There's always more to learn, and the journey of a Linux system administrator is one of continuous discovery. Summary and key takeaways. Linux is a pervasive, powerful, and open-source operating system that forms the backbone of the Internet, cloud computing, and many embedded devices. It originated from the Unix philosophy and was brought to life by Linus Torvalds and the GNU Project's tools. Linux is chosen for system administration due to its exceptional stability, robust security, unparalleled flexibility, cost-effectiveness, and strong community support. Linux distributions are complete operating systems built around the Linux kernel, offering different bundled software and philosophies, e.g., Debian/Ubuntu and Red Hat CentOS Stream families. A Linux system administrator is responsible for the installation, configuration, maintenance, security, and troubleshooting of Linux systems. Key skills include problem-solving, command line mastery, scripting, and networking. Your best learning environment will be a virtual machine lab, providing a safe space for hands-on practice. Further reading resources. The GNU project website, www.gnu.org. Learn more about the free software movement. The Linux Foundation, www.linuxfoundation.org. Explore the broader Linux ecosystem. Wikipedia pages for Linux, GNU project, Unix for historical context. Chapter 2, Getting Your Hands Dirty, Installation and First Login. In the previous chapter, we explored why Linux is the operating system of choice for system administrators and its pervasive presence in the digital world. Now, it's time to move from theory to practice. The best way to learn Linux system administration is by doing, and that begins with setting up your very own Linux environment. This chapter will guide you through preparing your learning lab, choosing a Linux distribution, performing an installation, and logging in for the first time. 2.1 Preparing your Linux lab. Imagine you're learning to drive a car. Would you immediately jump into traffic on a busy highway? Probably not. You'd start in a safe, controlled environment like a parking lot. Learning Linux administration is similar. We'll set up a lab where you can experiment, break things, and fix them without any real-world consequences to your primary computer. 2.1.1 The concept of virtualization. This safe learning environment is made possible by virtualization. At its core, virtualization allows you to run multiple operating systems simultaneously on a single physical computer. Your main computer, the one you're currently using, running Windows, Mac OS, or another Linux distribution, is called the host machine. The operating systems you install inside this host, like our new Linux server, are called guest machines or virtual machines, VMS. Think of virtualization software as creating a complete, simulated computer within your main computer. This simulated computer has its own virtual CPU, virtual memory, virtual hard drives, and virtual network interfaces, all allocated from your host machine's resources. Popular free virtualization software includes Oracle VirtualBox, open source, widely used, and available on Windows, Mac OS, and Linux. It's an excellent choice for beginners due to its ease of use and extensive community support. VMware Workstation Player, a free version of VMware's professional virtualization software, available for Windows and Linux. It's robust and often preferred in professional environments. For the purpose of this book, we will primarily refer to VirtualBox for our step-by-step examples, but the underlying concepts apply to other virtualization platforms as well. 2.1.2 Why use a virtual machine? Using VMS for your Linux lab offers several significant advantages. Safety, you can experiment freely. If you make a mistake that corrupts your Linux system, you can simply delete the virtual machine and start over without affecting your host computer. Experimentation, you can quickly set up and tear down different configurations, test various Linux distributions, or even simulate small networks of multiple Linux servers. Portability. Virtual machines can often be copied and moved between different host computers, making it easy to share your lab environment. Cost-effectiveness. It eliminates the need for dedicated physical hardware for each server you want to practice with. 2.1.3 Hardware requirements for virtualization. To run virtual machines smoothly, your host computer needs sufficient resources. Here are general guidelines. CPU. A modern multi-core processor, Intel Core i5, i7, or AMD Ryzen 5 7 equivalents or better. Crucially, your CPU must support virtualization technology, often called Intel VTX or AMDV. This is usually enabled in your computer's BIOS or UEFI settings. We'll discuss this more in the troubleshooting section. RAM. At least 8 GB of RAM is recommended for your host computer. This will allow you to comfortably allocate 2 to 4 GB to a virtual machine while leaving enough for your host OS. Storage. A solid-state drive, SSD, is highly recommended for faster performance. You'll need at least 20 to 30 GB of free disk space per virtual machine for a basic server installation. 2.2 Choosing your first Linux distribution. As we learned, a Linux distribution is a complete operating system built around the Linux kernel. For system administration, we primarily focus on server-oriented distributions, which are typically lean, stable, and designed for command line management. 2.2.1 Recommendation: Ubuntu Server or CentOS Stream. For your initial learning, we recommend one of two prevalent server distributions, Ubuntu Server. This is an excellent choice for beginners. It's based on Debian, known for its extensive software repositories, and has a very active community. Its installation process is straightforward, and it's widely used in cloud computing environments. You'll often hear about its package manager, apt, which makes software installation and updates very easy. CentOS Stream. This distribution is closely related to Red Hat Enterprise Linux, RHEL, which is a dominant force in corporate data centers. Learning CentOS Stream gives you valuable experience with the Red Hat ecosystem, including its DNF or older Yum package manager. It's known for its stability and enterprise focus. Both are excellent, relevant choices. This chapter will lean towards Ubuntu Server for the step-by-step installation due to its generally simpler setup for newcomers, but we will mention key differences for CentOS Stream. 2.2.2 Downloading the ISO image. A Linux distribution is usually distributed as an ISO image file. This is a single file that contains a complete snapshot of the operating system, structured like a DVD or CD. You'll download this file and mount it to your virtual machine as if it were a physical installation disk. To download your chosen ISO. For Ubuntu Server, visit the official Ubuntu website, e.g., www.ubuntu.com/download/server. Look for the latest long-term support, LTS, version, as these receive updates for many years and are more stable for server environments. You'll typically click a download button for the ISO file. For CentOS Stream, visit the official CentOS website, e.g., www.centos.org/centos-stream/. Navigate to the download section for CentOS Stream 9 or the latest stable version. You'll find links to download ISO images, often from mirror sites. Make sure to download the correct architecture, which for most modern computers will be AMD 64 or x86-64, 64-bit. The download size will typically be a few gigabytes, so it might take some time depending on your internet connection. Save the ISO file to a location you can easily find, like your Downloads folder. 2.3 Installing Linux on a Virtual Machine, Step-by-Step Guide. Now that you have your virtualization software and a Linux ISO, let's create your first virtual machine and install Ubuntu Server. Step 1. Install VirtualBox if you haven't already. Download and install Oracle VirtualBox from www.virtualbox.org. The installation process is straightforward, following the on-screen prompts. Step 2. Create a new virtual machine in VirtualBox. Open VirtualBox. Click the New button or select Machine New from the menu. Name and operating system. Name. Give your VM a descriptive name like Ubuntu Server Lab. Folder. You can accept the default or choose a different location for your VM files. ISO image. Click the drop-down, then Other, and navigate to where you saved your Ubuntu Server ISO file. Select it. VirtualBox might automatically detect the type Linux and version Ubuntu 64-bit based on the ISO. If not, set them manually. Check Skip Unattended Installation as we want to go through the manual steps. Click Next. Hardware, base memory, RAM, allocate at least 2048 MB, 2 GB for Ubuntu Server. For better performance, 4096 MB, 4 GB is even better if your host machine has enough RAM. Processors, allocate at least 2 CPU cores. Click Next. Hard disk. Create a virtual hard disk now, keep this selected. Disk size, allocate at least 20 GB. This is sufficient for a basic server installation and some room for work files. Click Next. Summary. Review your settings and click Finish to create the VM. Step 3. Start the virtual machine and begin installation. In the VirtualBox Manager window, select your newly created VM, Ubuntu Server Lab. Click the Start button, the green arrow. The VM will boot from the Ubuntu Server ISO. You might see a black screen with white text and a temporary menu. If presented with options, select Try or Install Ubuntu Server. Step 4. Go through the Ubuntu Server installation wizard. You'll be guided by a series of text-based screens. Use the arrow keys to navigate, the Tab key to move between elements, and the Enter key to select. Language. Choose your preferred installation language. Installer updates. Select Update to the new installer if prompted, assuming you have an internet connection. Keyboard configuration. Select your keyboard layout. Network connections. Ubuntu will usually detect a network adapter and attempt to configure it via DHCP, Dynamic Host Configuration Protocol, which automatically assigns an IP address. For now, this is sufficient. You'll see an IP address displayed. Make a note of it if you plan to use SSH later, e.g., emp03 10.0.2.15. Choose Done. Proxy address. Leave this blank unless you are in a corporate network that requires a proxy to access the internet. Choose Done. Mirror address. Accept the default mirror. Choose Done. Storage configuration. This is a crucial step. Guided storage configuration. For beginners, choose the Use an entire disk option. This will allocate the whole 20 GB virtual disk to Ubuntu. Warning. In a real-world physical server installation, use an entire disk would erase all data on that physical disk. In our virtual machine, it's safe because it's only affecting the virtual disk we just created. Review the file system layout, typically ext4 for the root file system and a swap partition. Confirm by selecting Done and then Continue when warned about erasing data. Profile setup. Your name, enter your full name. Your server's name, choose a host name like My Ubuntu Server. This is the name your server will use on the network. Pick a username, choose a login username, e.g., sysadmin. Choose a password, create a strong password. This will be your primary administrative password. Remember it, choose Done. SSH setup, install OpenSSH server. Select this option by pressing the spacebar and X will appear. This is vital because it allows you to remotely connect to your server from your host machine later, which is how most administrators manage Linux servers. Choose Done. Featured server snaps, you can skip this for now. These are additional software packages, but will install necessary ones later. Choose Done. Step 5. Installation process and reboot. The installer will now proceed to download and install packages. This can take several minutes depending on your internet speed and host machine performance. Once the installation is complete, you'll see a message, Install Complete. Choose Reboot Now. If the VM gets stuck after rebooting, saying, Please remove the installation medium, then press Enter. Go to your VirtualBox VM window menu, Devices Optical Drives, and uncheck the Ubuntu ISO. Then press Enter in the VM window. Your virtual machine will reboot, and you'll be greeted by a login prompt. 2.4 Your first login and exploration. After the reboot, you'll see something like this, though the exact text might vary slightly. Ubuntu 22.04, LTS, My Ubuntu Server TTY1. My Ubuntu Server Login. 2.4.1 The Login Prompt. This is your system's command line interface, CLI, also known as the terminal or console. This is where the vast majority of Linux system administration tasks happen. Unlike Windows or macOS, server Linux distributions typically don't have a graphical desktop environment unless you explicitly install one. Managing servers entirely through the command line is much more efficient and uses fewer resources. 2.4.2 Successfully logging in. At the login prompt, type the username you created during installation, e.g., sysadmin, and press Enter. At the password prompt, type your password. Important, as you type, nothing will appear on the screen, no asterisks, no dots. This is a security feature. Just type your password carefully and press Enter. If your credentials are correct, you'll see some system messages, possibly a welcome banner, and then your command prompt, which will look something like this. Sysadmin at my Ubuntu server $. Congratulations, you're logged into your very own Linux server. 2.4.3 Basic verifications. Let's run a few simple commands to confirm things are working. To check your hostname, type hostname and press Enter. Expected output, my Ubuntu server or whatever you named it. To check your IP address, type IP and press Enter. You'll see a lot of network information. Look for an entry similar to ANET 10.0.2.15/24 under your EMP03 or similar interface. This is your server's IP address within the virtual network. To learn where you are in the file system, type pwd, print working directory, and press enter. Expected output, home/sysadmin, this is your user's home directory. To list the contents of your current directory, type ls and press enter. Expected output, likely nothing yet or a very short list since it's a new home directory. We'll dive much deeper into these and many more commands in the next chapter. 2.5 Post-installation essentials. A fresh Linux installation is like a new car straight from the factory. It runs, but it needs a quick checkup and a few initial settings before you take it on a long road trip. 2.5.1 Updating system packages. This is the most critical first step after any Linux installation. Software packages are constantly being updated to fix bugs, improve performance, and patch security vulnerabilities. For Ubuntu and Debian-based systems, you use the apt command. First, update the list of available packages from the repositories. Sudo apt update. You'll be prompted for your password. Sudo stands for superuserdo and allows you to run commands with administrative privileges. Expect to see many lines of text showing it's fetching package lists. Next, upgrade all installed packages to their latest versions. Sudo apt upgrade. This command will list all packages that will be upgraded and ask for confirmation, y/n. Type Y and press enter. This process might take a while, depending on how many updates are available. For CentOS Stream and Red Hat-based systems, you use the dnf command, sudo dnf update. This single command updates the package lists and upgrades all packages. It will also ask for confirmation. Regularly running these update commands, e.g., daily or weekly, is a fundamental part of a system administrator's routine to keep systems secure and stable. 2.5.2 Installing essential utilities. Some useful tools might not be installed by default on a minimal server installation. A couple of common ones include NetTools provides older but still widely used networking commands like ifconfig for network interface configuration. While IP from iproute 2 is the modern replacement for ifconfig, many tutorials and older systems still use ifconfig. Sudo apt install NetTools for Ubuntu. Sudo dnf install NetTools for CentOS Stream, Vim or Nano. These are text editors for the command line. Nano is simpler and more beginner-friendly, while Vim is extremely powerful but has a steeper learning curve. Having at least one is essential for editing configuration files. Sudo apt install Nano for Ubuntu. Sudo dnf install Nano for CentOS Stream. Or for Vim, sudo apt install Vim for Ubuntu. Sudo dnf install Vim Enhanced for CentOS Stream. We'll briefly cover Nano in a later chapter to help you edit text files. 2.5.3 Configuring SSH. Since you enabled the OpenSSH server during installation, your Ubuntu server is already set up to accept remote connections. This is how most Linux systems, especially servers, are managed. Instead of typing directly into the VirtualBox window, you'll use an SSH client from your host machine. On Windows, you can use PowerShell or Command Prompt. Windows 10 and 11 have a built-in OpenSSH client or a dedicated client like poo-tty. On Mac OS or Linux, you already have a built-in SSH client in your terminal. To connect from your host machine, open your host machine's terminal, PowerShell Command Prompt on Windows, terminal on Mac OS Linux. Type SSH sysadmin at 10.0.2.15. Replace sysadmin with your chosen username, and 10.0.2.15 with the actual IP address you noted earlier using IP-a. The first time you connect, you'll be asked to confirm the authenticity of the host. Type yes and press enter. You'll then be prompted for your password. Type it and press enter. You should now see the familiar command prompt sysadmin at my Ubuntu server, $, but this time it's from your host machine's terminal. This is a much more convenient way to interact with your server, as you can use your host's clipboard for copy-pasting and generally a more comfortable interface. 2.6 Common installation pitfalls and troubleshooting. While virtualization software and Linux installers are robust, you might encounter a few common issues. 2.6.1 Virtualization Issues. VTX AMD not enabled. Problem: VirtualBox or VMware gives an error about VTX AMD hardware virtualization not enabled when trying to start a VM. Reason: your computer's CPU supports virtualization, but it's often disabled by default in the system's firmware, BIOS UEFI. Solution: you need to reboot your host computer and enter its BIOS UEFI settings. The key to enter BIOS UEFI varies by manufacturer. Common keys: F2, F10, F12, Dell-esque. Look for a setting related to virtualization technology, Intel VTX, AMD or SVM mode, and enable it. Save settings and exit. 2.6.2 Network connection problems. Problem: your VM doesn't get an IP address, or you can't reach the internet from inside the VM after installation. Reason: VirtualBox's network adapter settings might be misconfigured, or your host machine's network is blocking the VM. Solution: in VirtualBox, with your VM powered off, go to its settings network. Ensure Adapter 1 is enabled and Attached to is set to NAT, Network Address Translation. NAT is the default and usually easiest setup, allowing the VM to share your host's internet connection. Alternatively, Bridged Adapter can connect the VM directly to your physical network, making it appear as a separate device. This requires proper IP configuration. Start with NAT. After installation, ensure you ran sudo apt update or sudo dnf update to ensure correct repository access from within the VM. 2.6.3 Forgetting passwords. Problem: you forget the password for your user or the root password during installation. Reason: human error, it happens. Solution: for a VM, the simplest solution is often to delete the VM and reinstall. You'll gain practice, and it's quicker than complex password recovery processes for a new system. For production systems, password recovery methods exist, but they are more involved and outside the scope of initial setup. 2.6.4 Disk partitioning errors. Problem: the installer complains it can't partition the disk, or you accidentally make a wrong choice during storage configuration. Reason: incorrect selection, or in rare cases, a problem with the virtual disk image. Solution: ensure you selected use an entire disk and confirmed the erasure. If problems persist, try creating a new virtual hard disk for the VM in VirtualBox, or even deleting and recreating the entire virtual machine. Remember, practice is key. Don't be afraid to try multiple installations. Each time you'll become more familiar with the process and the options available. The more comfortable you become with the setup, the more capable you'll be when it's time to tackle administration tasks. Summary and key takeaways. A Linux lab using virtual machines, VMS, is the safest and most effective way to learn Linux system administration. VirtualBox or VMware Workstation Player are excellent free virtualization software options. Ensure your host computer has sufficient CPU, with virtualization enabled, RAM, and storage. Ubuntu Server and CentOS Stream are highly recommended server distributions for learning. Download their ISO image files. The installation process typically involves creating a new VM, attaching the ISO, configuring networking, usually DHCP initially, setting up disk partitioning, using the entire virtual disk for simplicity, creating your user, and installing the OpenSSH server. After installation, the most important first steps are to update all system packages, sudo apt update, and in sudo apt upgrade for Ubuntu, or sudo dnf update for CentOS Stream, and install useful utilities like a command line text editor, Nano. SSH allows you to remotely connect to and manage your Linux server from your host machine's terminal. Common troubleshooting steps involve checking BIOS UEFI for virtualization settings, verifying VirtualBox network adapter settings, and when in doubt, reinstalling the VM. Practical exercise. Following the instructions in this chapter, install Ubuntu Server in VirtualBox. Ensure you allocate at least 2 GB RAM and 2 CPU cores to the VM. Select Use an entire disk for storage. Install the OpenSSH server during setup. After installation, use sudo apt update and sudo apt upgrade to update all packages. Install the Nano text editor. From your host machine, successfully connect to your new Linux server using SSH. Further reading resources. Oracle VirtualBox User Manual. www.virtualbox.org/manual/user-manual-html for in-depth VirtualBox configuration. Ubuntu Server Documentation. ubuntu.com/server/docs. CentOS Stream Documentation. docs.centos.org/n-us/centos-stream/. Chapter 3. The Command Line Awakens. Navigating with Power. In the last chapter, you successfully installed your first Linux server and even connected to it remotely via SSH. Now, it's time to unlock the true power of Linux administration, the command line. While graphical interfaces are convenient for desktop users, the command line is the heart and soul of server management. Mastering it is perhaps the most fundamental skill for any Linux administrator. 3.1 Why the command line? The administrator's superpower. To someone accustomed to clicking icons and dragging windows, the command line might seem daunting at first. It's a blank screen, waiting for your instructions. But this apparent simplicity hides immense power and efficiency. 3.1.1 Efficiency for repetitive tasks. Imagine you need to create 100 new user accounts, each with similar settings. In a graphical user interface, this would involve 100 sets of clicks, typing, and confirming. On the command line, you might write a single command or a short script that automates the entire process in seconds. This principle scales enormously in a large data center. 3.1.2 Automation Potential. The command line is the language of automation. Every command you execute can be strung together with others, saved in a file as a script, and run automatically at scheduled times. This allows administrators to set up routine tasks like backups, log cleanups, and system health checks to run without manual intervention. 3.1.3 Remote Management (SSH). Most Linux servers are managed remotely, often across continents. When you connect via SSH, you're interacting with a command line interface. There's no graphical interface to load or maintain, making remote management lightweight and reliable even over slow network connections. 3.1.4 Resource Efficiency. No GUI overhead. A server's primary purpose is to run services, not to look pretty. Graphical desktop environments consume significant system resources, CPU, RAM, disk space. By operating purely in the command line, Linux servers can dedicate almost all their power to the applications they host, leading to greater efficiency and stability. This is why you typically don't install a desktop environment on a server. 3.2 Understanding the Linux Shell Bash. When you log into your Linux system and see the cursor blinking, you are interacting with a shell. A shell is a program that provides an interface for users to execute commands and scripts. The most common shell on Linux, and the one we'll be using, is Bash, born again shell. 3.2.1 What is a shell? Interpreter. Think of the shell as an interpreter. You type commands in plain text, and the shell translates those commands into instructions that the Linux kernel can understand and execute. It also manages command history, input-output, and provides features like tab completion. 3.2.2 The prompt, user, host, current directory, shell indicator. When you log in, you see a command prompt. It typically looks something like this: sysadmin at my Ubuntu server $. Let's break down what each part signifies. Sysadmin, this is your current username. A separator, my Ubuntu server. This is the host name of the system you're logged into. Another separator. This symbol represents your current working directory. The tilde is shorthand for your home directory, e.g., home/sysadmin. If you were in a different directory, the full path or part of it would be shown here. $. This is the shell indicator. For a regular user, it's typically a $sign. If you were logged in as the powerful root user, the superuser, it would be a hash symbol, indicating elevated privileges. Every time you see this prompt, it means the shell is ready for your next command. 3.3 Basic Command Structure. Nearly all Linux commands follow a simple, consistent structure. Command options arguments. Command. This is the name of the program or utility you want to run, e.g., ls to list files, cd to change directories. Options, also called flags or switches, these modify the behavior of the command. Options begin with a hyphen or double hyphen. They are enclosed in square brackets in the syntax, indicating they are optional. Arguments, these are the inputs the command acts upon, such as file names, directory paths, or usernames. Arguments are also optional, depending on the command. 3.3.1 Short versus long options, AVs all. Most commands offer two forms of options. Short options, single letters preceded by a single hyphen, e.g., a. Multiple short options can often be combined, e.g., la is the same as la. Long options, full words preceded by two hyphens, e.g., all. These are more descriptive, but cannot usually be combined. Both forms achieve the same result. You'll often use short options for speed and long options for clarity, or when specific functionality is only available via a long option. 3.4 Navigating the file system. The Linux file system is organized hierarchically, like an upside-down tree, starting from the root directory, symbolized by a single /. Everything on the system resides under this root. 3.4.1 PWD, Print Working Directory. The PWD command tells you where you currently are in the file system. It stands for Print Working Directory. Type PWD and press Enter. Expected output, home/sysadmin, assuming your username is sysadmin. 3.4.2 ls, list directory contents. The ls command lists the contents of a directory. By default, it lists files and directories in your current working directory. Type ls and press Enter. Expected output, likely nothing if your home directory is empty, or a few default directories like desktop, documents, etc. if you chose a desktop install, which we did not. Let's try some useful options with ls. LSL, the long listing format. This provides detailed information about each file directory, including permissions, owner, group, size, and modification date. LSA, list all files, including hidden ones. Hidden files begin with a dot. For example, bashrc is a common hidden configuration file. LSH, used with L, it provides human-readable file sizes, e.g., 10K instead of 10,240. So LSLH is a very common and useful combination. LSF appends a character to entries to indicate their type, e.g., for a directory, for an executable. Try LSLOF. This will give you a comprehensive view of everything in your current directory. 3.4.3 CD, Change Directory. The CD command allows you to change your current working directory. CD, changes to the root directory. CD, changes to your home directory, same as CD without any arguments. CD, changes to the parent directory, one level up. CD path to directory, changes to an absolute path, starting from the root. CD another directory, changes to a relative path, relative to your current location. Let's practice. Type CD and press Enter. Your prompt will change to type PWD and press Enter. Output, type ls and press Enter. You'll see system directories like bin, etc., home, var, etc. Type CD home and press Enter. Your prompt will change to home. Type ls and press Enter. Output, sysadmin. Type CD sysadmin and press Enter. Your prompt will change to / or home/sysadmin. You are back in your home directory. Type CD and press Enter. You are now in home. Type CD and press Enter. You are now back at the root. Type CD and press Enter. You are back in your home directory. 3.5 Managing Files and Directories. Now that you can navigate, let's learn how to create, copy, move, and delete files and directories. First, make sure you are in your home directory, CD. 3.5.1 Touch, create empty files or update timestamps. The touch command creates new, empty files. If the file already exists, touch updates its latest modification timestamp. Type touch myfirstfile.txt and press Enter, then LSL. You'll see myfirstfile.txt listed with the current date time. 3.5.2 mkdir, make directories. The mkdir command creates new directories. Type mkdir mydocuments and press Enter. Type ls. You'll see mydocuments listed. To create multiple nested directories at once, use the P option. Type mkdir pprojects/web/frontend and press Enter. Type ls projects. You'll see web. Type ls projects web. You'll see frontend. 3.5.3 CP. Copy files and directories. The CP command copies files or directories from one location to another. Type CP, myfirstfile.txt, mysecondfile.txt, and press enter. Copies myfirstfile.txt and names the copy mysecondfile.txt. Type ls. You'll see both files. To copy a file into an existing directory, type cp myfirstfile.txt, mydocuments / and press enter. Type ls mydocuments. You'll see myfirstfile.txt inside. To copy directories, you must use the recursive option R. Type cpr projects pickup / and press enter. Type ls. You'll see projects pickup. Type ls projects pickup / web / frontend. You'll see the nested structure was copied. 3.5.4 mv, move rename files and directories. The mv command moves files or directories. It's also used to rename them. To rename a file, type mv mysecondfile.txt, renamed file.txt, and press enter. Type ls. Mysecondfile.txt is gone, renamed file.txt appears. To move a file into a directory, type mv renamed file.txt mydocuments / and press enter. Type ls. Renamed file.txt is gone, type ls mydocuments. You'll see renamed file.txt moved there. The mv command works the same way for directories, just specify the directory name as the source. 3.5.5 rm, remove files. The rm command removes files. Be careful with rm. It does not move files to a recycle bin or trash. Once you rm something, it's gone. To remove a single file, type rm mydocuments / myfirstfile.txt and press enter. Type ls mydocuments. Myfirstfile.txt is no longer there. You might be prompted for confirmation if the file is write protected, e.g., rmis. To force removal without prompting use with extreme caution, use f.e.g. rm f file.txt. 3.5.6 rmdir. Remove empty directories. The rmdir command removes empty directories. If a directory contains files or other directories, rmdir will fail. Type rmdir projects pickup / web / frontend and press enter. Type rmdir projects pickup / web and press enter. Type rmdir projects pickup and press enter. This would only work if projects pickup was empty after removing its subdirectories one by one. To remove directories that are not empty and all their contents, you must again use the rm command with the recursive option R. Type rm projects and press enter. Type ls. The projects directory is gone. Practical example, organizing your Linux lab. Let's create a small structure to practice. cd, go to your home directory. mkdir documents photos scripts. Touch documents / report.txt documents / notes.txt. Touch photos vacation. .jpg photos / family png. Touch scripts / backup sh. lsf, see your new directories. ls documents, see the files inside documents. Now, let's simulate a mistake and fix it. You accidentally created vacation.jpg in documents instead of photos. mv documents vacation.jpg photos, move the file. ls documents, confirm it's gone from documents. ls photos, confirm it's now in photos. 3.6 Viewing file contents. Often, you'll need to quickly inspect the contents of a text file, like a configuration file or a log file. 3.6.1 Cat, concatenate and display. The cat command, short for concatenate, displays the entire content of a file to your screen. It's best for small files. Let's create a simple file to view. Type echo, this is the first line. Test.txt and press enter. Type echo, this is the second line. Test.txt and press enter. Now view it. Type cat test.txt and press enter. Expected output. This is the first line. This is the second line. 3.6.2 Less and more paginated viewing. For larger files, e.g. long log files, cat will scroll the content past your screen quickly. Less and more allow you to view content one screen at a time. Less is generally preferred as it allows you to scroll both forwards and backwards. Imagine you have a large log file. Type lessvar /log /syslog and press enter. Use the spacebar to move forward one screen. Use the B key to move backward one screen. Use the down arrow and up arrow keys to scroll line by line. Type followed by text to search forward, e.g. error. Press Q to quit less. More is similar but generally only allows forward scrolling. Learning less will cover most of your needs. 3.6.3 Head and Tail. Viewing beginning and end. Head displays the beginning of a file, tail displays the end. Both are especially useful for log files, where you often want to see the most recent entries. By default, they show the first or last 10 lines. Use the N option to specify a different number of lines. To see the first 5 lines of a file, type head N5 testfile.txt. To see the last 15 lines of a log file, type tail N15/var/log/syslog. A very common use of tail is with the F follow option, which outputs new lines as they are added to the file. This is crucial for real-time monitoring of active log files. Type tail fvar/log/cloudinit output log if you have this file. This command will keep running, showing you new lines as they appear. To stop it, press Ctrl+C. Practical example. Inspecting common system files. Try viewing some common Linux system files. Cat etc. os release shows information about your operating system distribution. lesvar/log/auth-log. Inspect authentication attempts. Head n10/etc/password. View the first 10 lines of the user database file. 3.7 Input-output redirection and pipes. One of the most powerful features of the Linux command line is the ability to redirect the output of commands and chain them together. 3.7.1 Standard output, standard input, standard error. Every command in Linux typically deals with 3 data streams. Standard output, stdout. The normal output of a command, e.g., the list of files from ls. This usually goes to the screen. Standard input, stdin. The input a command expects, e.g., text you type. This usually comes from the keyboard. Standard error, stdir. Error messages generated by a command. This usually goes to the screen. 3.7.2 Redirecting output to a file. You can save the standard output of a command to a file instead of displaying it on the screen. Redirects output and overwrites the file if it exists. If the file doesn't exist, it creates it. Type ls lfiles.txt and press enter. Type cat files.txt. You'll see the output of lsl saved in the file. Redirects output and appends to the end of the file if it exists. If the file doesn't exist, it creates it. Type date files.txt and press enter. Type cat files.txt. You'll see the date added after the original lsl output. This is extremely useful for generating reports, saving configuration settings, or capturing command output for later analysis. 3.7.3 Redirecting input from a file. Less common in day-to-day administration, but you can also direct the content of a file as input to a command. Example: cat filename.txt is essentially the same as cat filename.txt. 3.7.4 The power of pipes. The pipe symbol takes the standard output of one command and sends it as the standard input to another command. This allows you to chain commands together to perform complex tasks. Imagine you want to count the number of lines in a file. Type cat files.txt wcl and press enter. First, cat files.txt outputs the file's content. Then, takes that output and feeds it as input to wcl word count command with the line count option. The result is just the number of lines. This is incredibly powerful. Let's find all processes running on your system that contain SSH in their name. Type ps-aux grep SSH and press enter. ps-aux lists all running processes. This generates a lot of output. Pipes that output. grep SSH filters the input it receives and only displays lines that contain the word SSH. You'll see output related to the SSH server you installed and possibly your own SSH connection. This combination, command grep pattern, is perhaps one of the most frequently used command line patterns. 3.8 Essential command line productivity tips. Becoming efficient at the command line isn't just about knowing commands. It's also about typing them quickly and accurately. 3.8.1 Tab completion, speed and accuracy. This is perhaps the biggest time saver. When you're typing a command, file name, or directory, you can press the tab key to autocomplete. If there's only one possible completion, Bash will fill it in. If there are multiple possibilities, press tab twice and Bash will show you all options. Try it, Type cd-mydoc then press tab. It should autocomplete to cd-mydocument/. Type ls then space, then scry then press tab twice. It will show you scripts type p and then press tab. It will complete scripts use tab completion constantly. It prevents typos and saves keystrokes. 3.8.2 Command History, Arrow Keys, History Command. Bash keeps a history of the commands you've typed. Use the up arrow key to cycle through previous commands. Use the down arrow key to cycle forward. Type history and press enter to see a numbered list of all commands you've recently executed. You can then use n, where n is the number from history, to re-execute a specific command. For example, 10 would rerun the 10th command in your history list. To search through history, press Ctrl+R and start typing characters. Bash will show you the most recent command that matches what you're typing. Press Ctrl+R again to find older matches. This feature is invaluable for recalling complex commands or correcting mistakes without retyping. 3.8.3 Wildcards. Wildcards are special characters that represent one or more other characters, allowing you to operate on multiple files with a single command. Asterisk matches 0 or more characters. ls.txt lists all files ending with txt. rm report deletes all files starting with report. Question mark matches exactly one character. ls file, txt. Matches file 1, txt, file 8 txt, but not file 10 txt. Square brackets matches any single character within the brackets. ls abc file txt. Matches a file txt, b file txt, or c file txt. ls 0 to 9 log matches 1 log, 2 log, etc. 3.9 Getting help. The man pages. Linux has excellent built-in documentation, known as man pages, manual pages. Every command, configuration file, and system call has a corresponding man page. 3.9.1 How to use man. To access a command's man page, type man followed by the command name. Type man ls and press enter. You'll see a detailed description of the ls command, its synopsis, options, examples, and related commands. You'll navigate man pages using the same keys as less, spacebar for next page, B for previous, Q to quit. 3.9.2 Interpreting man page sections. Man pages are typically structured into sections. Name, the name and a brief description of the command. Synopsis, how to use the command, showing its syntax, options, and arguments. Optional items are enclosed in square brackets. Description, a detailed explanation of what the command does. Options, an explanation of each available option. Examples, practical examples of how to use the command. See also, related commands or man pages. 3.9.3 The help option for quick summaries. Many commands also support a help option, or just H for some simple commands, that provides a quick, concise summary of its usage and common options directly in the terminal, without opening the full man page. Type ls, help, and press enter. This is often faster than man when you just need a reminder of an option. 3.10 Common command line hurdles and troubleshooting. Even experienced administrators make typos. Knowing how to interpret common errors will save you a lot of frustration. 3.10.1 Command not found errors. Error, command name, command not found. Reason, you typed the command incorrectly, or the command is not installed on your system, or it's not in your shell's path, the list of directories where the shell looks for executable commands. Solution, check for typos. Did you mean ls instead of sla? Is the command part of a package that needs to be installed? For example, ifconfig is part of NetTools and might not be installed by default on newer systems. If you're sure the command exists, it might not be in your path. This is less common for standard commands, but can happen with custom scripts or newly installed software not properly configured. 3.10.2 Incorrect paths and typo mistakes. Error, no such file or directory. Reason, you specified a file or directory path that does not exist or is misspelled. Solution, double-check your spelling and capitalization. Linux file systems are case-sensitive. My folder is different from my folder. Verify the path. Is it an absolute path starting from, or is it a relative path from your current directory? Use ls to list the contents of the directories in the path to identify where the error is. Always use tab completion to minimize these errors. 3.10.3 Understanding error messages. Don't be intimidated by error messages. They are often your best clues for troubleshooting. Read them carefully. Many contain keywords, file paths, or line numbers that point directly to the problem. Over time, you'll learn to quickly identify the root cause of common errors based on the message. The command line is your primary interface to the Linux server. Practice these commands regularly. The more you use them, the more intuitive they will become, transforming from a daunting blank screen to a powerful tool at your fingertips. Summary and key takeaways. The command line interface, CLI, is the most efficient and powerful way to manage Linux servers, allowing for automation and remote administration. The shell bash is the program that interprets your commands and interacts with the Linux kernel. Basic command structure is command options arguments. Options modify command behavior, all, and arguments are the inputs. Navigate the file system using pwd, print working directory, ls list contents, lsl for long format, lsa for all, lsh for human readable sizes, lsf for type indicators. cd, change directory, cd. For parent, cd for home, cd for root. Manage files and directories using touch create empty file. mkdir, make directory, mkdir, p for parent directories. cp copy, cpr for directories. mv, move or rename. rm, remove files, no trash recycle bin. rmr for non-empty directories, rmf to force. rmdir, remove empty directories. View file contents using cat display entire file for small files. Less paginated viewer, use space to advance, b to go back, q to quit. Head first in lines, head nn. Tail last in lines, tail nn. Tail f to follow new entries in real time. Redirect command output with overwrite, or append to a file. Chain commands together using pipes, sending the output of one command as input to another, e.g., ps aux grep ssh. Boost productivity with tab completion for commands and file paths and your command history, up-down arrows, history command. Get help with man command name for detailed manual pages or command name help for quick summaries. Common troubleshooting steps include checking spelling, verifying paths, and carefully reading error messages. Practical exercise. Command line scavenger hunt and file manipulation. Using your Ubuntu server VM and the knowledge from this chapter, complete the following tasks. Use ls and pwd frequently to verify your location and contents. Navigate, go to the root directory, go to the /var directory, go to the /var/log directory, go back to your home directory. Create and organize. In your home directory, create a new directory named myadminwork. Inside myadminwork, create two subdirectories, configfiles and scripts. Create an empty file named newscript.sh inside the scripts directory. Create an empty file named serversettings.conf inside the configfiles directory. Copy and rename. Copy newscript.sh from the scripts directory into your home directory, still named newscript.sh. Rename the copied newscript.sh in your home directory to tempscript-back. View and search. Use cat to view the contents of etc. os release. Use less to view var/log/syslog. Scroll around, use to search for error, and then quit. Use tail n5/etc/password to see the last 5 lines of the user database. Use a pipe to find all files in your home directory, LSL, that contain the word script, grep. Clean up, delete the tempscript-back file from your home directory. Delete the entire myadmin work directory and all its contents. Remember to use the necessary option for non-empty directories. Further reading resources. Bash Reference Manual. www.new.org/savannah-checkouts/new/bash/manual/bash-html. For advanced users seeking deep dives into Bash features. Online Linux command reference sites, e.g., linuxcommon.org, ss64.com/bash/. Chapter 4. Files, Directories, and Permissions, the Linux Foundation. You've learned to navigate the command line and issue basic commands. Now, it's time to delve into the very structure upon which Linux operates, its file system. Understanding how files and directories are organized, and crucial, how their permissions are controlled, is fundamental to effective system administration and security. In Linux, everything is treated as a file, from documents and images to hardware devices and running processes. This consistent approach simplifies management, but demands a clear understanding of its underlying principles. 4.1 The Linux File System Hierarchy (FHS). Unlike some operating systems where different drives, like C or D, may contain separate file systems, Linux organizes all files and directories under a single, unified tree structure starting from the root directory, denoted by a single /. This standardized layout is guided by the File System Hierarchy Standard, FHS, which defines the purpose of various directories. This consistency means that whether you're working on Ubuntu, CentOS, or any other major Linux distribution, you'll find the core directories in predictable places. Let's explore some of the most important top-level directories. The root directory. This is the top of the file system hierarchy. All other directories and files are located under this directory. Bin and /usr/bin contain essential user executable programs, commands. For example, ls, cp, mv are likely found here. Usr/bin typically holds more non-critical commands. /sbin and /usr/sbin contain system binaries, commands, that are typically used by the root user or system administrators for system administration tasks, e.g., fdisk, reboot, IP, etc. Contains system-wide configuration files. This is a crucial directory for administrators, as modifying files here often changes how the system behaves, e.g., network settings, user configuration, application settings. Home contains the personal home directories for regular users. When you log in as sysadmin, your home directory is home/sysadmin. This is usually where users store their documents, downloads, and personal configurations. var stands for variable data. This directory holds data that changes frequently during system operation. Examples include var/log, system log files, e.g., syslog, authlog. These are incredibly important for troubleshooting and security auditing. var/www, default location for web server data. var/mail, user mailboxes. /usr stands for Unix system resources. This is a large and important directory containing shareable, read-only data. It often holds most of the user applications, libraries, documentation, and source code. Opt stands for optional. This directory is reserved for the installation of third-party, add-on software packages that are not part of the standard distribution. /tmp contains temporary files created by users and the system. Files in /tmp are often deleted on system reboot or after a certain period. Dev stands for devices. This directory contains device files that represent physical hardware devices, e.g., /dev/sda for a hard drive, dev/null for a black hole. These are not devices themselves, but rather interfaces to them. Proc stands for processes. This is a virtual file system that provides information about running processes and kernel parameters. It's not stored on disk, but generated dynamically by the kernel. /mnt and media, common mount points for temporary file systems, such as USB drives, CDS, or network shares. Media is often used for removable media, while /mnt is for more persistent temporary mounts. Understanding this hierarchy streamlines directory navigation and helps you quickly locate important files, especially configuration and log files. 4.2 Understanding paths, absolute versus relative. When working with files and directories, you need to specify their location using a path. There are two main types of paths: absolute paths. An absolute path always starts from the root directory, / and specifies the entire path to a file or directory. No matter where your current working directory is, an absolute path will always point to the same location. Analogy. This is like giving someone a full postal address, including the country, city, street, and house number. Example: home/sysadmin/documents/report.txt. Relative paths. A relative path specifies the location of a file or directory relative to your current working directory. It does not start with a /. Analogy. This is like giving directions from where you are standing right now, such as go 2 blocks down, then turn left. Example. If your current directory is home/sysadmin, then documents/report.txt refers to the same file as the absolute path home/sysadmin/documents/report.txt. Special relative path notations represents the current directory. E.g., /misscript.sh to run a script in the current directory, or cp/file1 txt/file2 txt to copy within the current directory. Represents the parent directory, one directory level up. E.g., cd to go up one directory. Practice using both types of paths as you navigate your system. Absolute paths are safer for scripting or when you need to be certain of the target, while relative paths are often quicker for interactive use within a confined area. 4.3 Linux file types. In Linux, a file isn't just a document or a program. The lsl command, which provides a long listing format, displays detailed information about files, including their type. The very first character in the permissions string, which we'll discuss next, indicates the file type. Hyphen, a regular file. This is the most common type, including text files, binary executables, images, archives, and so on. D. A directory. This is a special type of file that contains references to other files and directories. L. A symbolic link, symlink, or soft link. This is essentially a shortcut or pointer to another file or directory elsewhere in the file system. If the original file is deleted, the link becomes broken. B. A block device file. Represents devices that transfer data in fixed-size blocks, such as hard drives, /dev/SDA, CD-ROM drives, /dev/SR0, or USB drives. C. A character device file. Represents devices that transfer data character by character, such as serial ports or a terminal /dev/TTY0. S. A socket file. Used for interprocess communication, allowing unrelated processes to communicate with each other. P. A named pipe FIFO. Also used for interprocess communication, allowing processes to communicate sequentially. When you run lsl, look at the first character to quickly identify what kind of file you're dealing with. For instance, drwxrxrx indicates a directory, rwrr indicates a regular file, and lrwxrwxrwx indicates a symbolic link. 4.4 File and directory permissions. The gatekeepers. Permissions are the cornerstone of Linux security and essential for multi-user environments. They control who can do what with a file or directory. The lsl command is your window into these permissions. Let's break down the rwxrxrx string you see in an lsl output. rwxrxrx. This 10-character string provides all the permission information. First character, file type. As discussed, this indicates the file type, e.g., for regular file, D for directory. Next 9 characters, permissions. These 9 characters are organized into 3 sets of 3 characters each, controlling permissions for the owner, first set of 3, the user who owns the file or directory, the group, second set of 3, the group that owns the file or directory, others, third set of 3, everyone else on the system who is not the owner and not part of the owning group. Each set of 3 represents the read R, write W, and execute X permissions. Read R, for a file, allows viewing the file's content. For a directory, allows listing the files and subdirectories within that directory. Write W, for a file, allows modifying, saving changes to, or deleting the file. Deleting a file also depends on permissions of its parent directory. For a directory, allows creating, deleting, or renaming files within that directory. This is a critical distinction. To delete a file, you need write permission on the directory it's in, not just on the file itself. Execute X, for a file, allows running the file as a program or script. Without execute permission, you cannot run a script, even if you can read its contents. For a directory, allows entering the directory using cd and accessing its contents. Without execute permission on a directory, you cannot cd into it or access files inside, even if you have read permission. If a permission is not granted, a hyphen appears in its place. Example: rwxrxrx, owner, rwx, read, write, execute. Group rx read execute no write. Others rx read execute no write. 4.5 Understanding permission notation, octal and symbolic. When you change permissions, you can use two primary notation methods, symbolic and octal numeric. 4.5.1 Symbolic mode, UGO RWX. This method uses letters and operators to describe permission changes. Who, U user owner, G group, O others, A all you go. Action plus add permission, remove permission, equals set exact permission, overriding current settings. Permissions, R read, W write, X execute. Examples of symbolic mode. Chmod U plus X misscript sh, add execute permission for the owner of misscript sh. Chmod go W myfile.txt. Remove write permission for the group and others from myfile.txt. Chmod U equals rwx go equals rx mydir. Set owner permissions to read, write, execute. Set group and others permissions to read and execute for mydir. 4.5.2 Octal numeric mode. This method uses numbers to represent permissions and is often preferred for its precision and conciseness, especially in scripting. Each permission type is assigned a numerical value. R read equals 4. W write 2. X execute equals 1. No permission equals 0. To get the octal value for each set, owner, group, others, you sum the values of its permissions. Examples of octal values. RWX equals 4 plus 2 plus 1 equals 7. RW equals 4 plus 2 plus 0 equals 6. RX equals 4 plus 0 plus 1 equals 5. R equals 4 plus 0 plus 0 equals 4. X equals 0 plus 0 plus 1 equals 1. Equals 0 plus 0 plus 0 equals 0. So, a permission string like RWXRXRX translates to 755, 7 for owner, 5 for group, 5 for others. A common permission for simple files is RWRR, which is 644. 4.6 Changing permissions, the chmod command. The chmod, change mode, command is used to modify file and directory permissions. Let's demonstrate with examples. First, create a dummy file and script in your home directory, touch dummy.txt, touch misscript sh. Now, check their initial permissions. ls l dummy.txt misscript sh. Output similar to rwrwr1 sysadmin appr 2310 0 dummy.txt. rwrwr1 sysadmin appr 2310 0 misscript sh. Note, the actual default permissions might vary slightly depending on your system's umask setting, which dictates default permissions for new files directories. Changing with symbolic mode. Make misscript sh executable for the owner. Chmod U plus X misscript sh. LSL misscript sh. Output RWXRWR. Notice the X for owner. Remove write permission for everyone on dummy.txt. Chmod AW dummy.txt. LSL dummy.txt. Output RRR, no W anywhere. Set specific permissions for a directory, mkdir privatedata. Chmod U equals RWX go equals privatedata. This is equivalent to chmod 700 privatedata. LSL grep privated. Output, DRWX, only owner has full access. Changing with octal mode. Make misscript sh read write execute for owner, read execute for group and others, common for scripts. Chmod 755, misscript sh. LSL misscript sh. Output RWXRXRX. Make dummy.txt read write for owner, read only for group and others, common for data files. Chmod 644 dummy.txt. LSL dummy.txt. Output RWRR. Make a directory accessible only to the owner, maximum privacy. Chmod 700 privatedata. This achieves the same as chmod U equals RWX go equals. 4.7 Changing ownership, chown and chgrp. Beyond permissions, every file and directory in Linux has an owner, a user, and an owning group. Only the root user or the current owner, for group changes, can change file ownership. 4.7.1 Chown, change owner. The chown command changes the owner of files or directories. It can also change the owning group simultaneously. You will typically need sudo or be logged in as root to use chown. Change user owner, sudo chown user misscript sh. This changes the owner of misscript sh to user. Change group owner only. Sudo chown, new group miscript sh. This changes only the group of miscript sh to new group. Change both user and group owner. Sudo chown user, new group miscript sh. Change ownership recursively for directories and their contents. Sudo chown r user, new group path to directory, use r for recursive. Practical use case. Imagine a web server user, often named www.data, on Debian/Ubuntu, or Apache, on Red Hat CentOS. If your website files are uploaded by sysadmin, but the web server needs to read them or even write to a specific directory, like for uploads or logs, you might need to change ownership. Sudo chown r www.data, www.data/var/www/html. 4.7.2 chgrp, change group. The chgrp command is a simpler version of chown that changes only the group owner of files or directories. You generally need to be the owner of the file or root to use this. Change group owner. Sudo chgrp new group dummy.txt. Change group owner recursively. Sudo chgrp r new group path to directory. While chown, new group can achieve the same as chgrp. chgrp is often used for clarity when only the group needs to be modified. 4.8 Special permissions, briefly for awareness. Beyond the standard RWX permissions, Linux has 3 special permission bits that offer powerful, but potentially dangerous, capabilities. You'll encounter these on pre-existing system files or in specific administrative scenarios. SUID, set user ID, indication, and S appears in the owner's execute position, e.g. rwsrxrx. Effect. When an executable file with SUID set is run, it executes with the permissions of the owner of the file, not the user who ran it. Example. The passwd command, which allows regular users to change their password, needs to write to a restricted system file that only the root user can modify. Passwd has the SUID bit set, so when a regular user runs it, the program briefly executes as root to perform the password change. Why it's dangerous. If a malicious program has SUID set and is owned by root, any user executing it could gain root privileges. SGID, set group ID. Indication. An S appears in the group's execute position, e.g. rwxrsrx. Effect on files. Similar to SUID, an executable with SGID set runs with the permissions of the file's group. Effect on directories, more common. Any new files or subdirectories created within an SGID-enabled directory will automatically inherit the group ownership of the parent directory, rather than the primary group of the user who created them. This is extremely useful for shared directories where multiple users need to collaborate. Example. For a project directory where all team members need group write access and new files should maintain the project group's ownership. Sticky bit, indication. A T appears in the other's execute position, e.g. drwxrwxrwt. Effect on directories, most common use. Users can create, read, and write files within that directory. However, a user can only delete or rename files they own or files where they have explicit write permission. Even if a user has write permission on the directory, they cannot delete other users' files within it. Example. The /tmp directory almost always has the sticky bit set. This ensures that while everyone can create temporary files, they can't delete another user's temporary files. While these special permissions are powerful, chmod can set them using octal values. SUID. Add 4000 e.g. chmod 4755 miscript sh. SGID. Add 2000 e.g. chmod 2755 mydear. Sticky. Add 1000 e.g. chmod 1777/tmp. For everyday administration, understanding the RWX permissions and how to change them with chmod, numeric and symbolic, and chown/chgrp is paramount. 4.9 Practical applications and troubleshooting permissions. One of the most common frustration points for new Linux administrators is the elusive permission denied error. Mastering permissions is key to diagnosing and resolving these issues. Permission denied troubleshooting steps. When you encounter permission denied, while trying to access a file, directory, or execute a command, systematically check the following. Who is trying to access? Identify the user account attempting the operation. If it's a service, like a web server or database, understand which user account that service runs as, e.g., www data MySQL. Check the target's permissions, LSL, run LSL path to thing file directory or LSL path /to /parent directory if the issue is creating deleting. Is the user the owner? If so, check the owner's permissions, RWX. Is the user a member of the owning group? Run group's username to see the groups your user belongs to. If so, check the group's permissions, RWX. Is the user neither owner nor in the owning group? Then they fall under others, so check others' permissions, RWX. Does permission allow the action? Read access. Is R bit set? Write access. Is W bit set and W set on parent directory for creating deleting? Execute access. Is X bit set for files to run them or for directories to CD into them or access contents? Check parent directory permissions for files within a directory. Even if a file has RW for others, if the directory it's in only has execute permission X for others, you won't be able to list its contents, hence won't see the file to read it. To copy or save a file into a directory, you need W and X on that directory. Scenario example: you've created a log directory for an application, var/log/mywebapp. lsld var/log/mywebapp shows drwxrxr, root owns it, root group owns it. Your web application runs as www data. It tries to write logs to this directory and gets permission denied. Troubleshooting: www data is not root, and www data is probably not in the root group. So www data falls under others. Permissions for others are R read-only. The application needs W write permission. Solution 1 ideal. Change the group ownership of mywebapp to www data and grant group write. Sudo chown root www data var/log/mywebapp. Sudo chmod g+ w var/log/mywebapp. Or sudo chmod 775/var/log/mywebapp. This maintains root ownership, but grants www data group write access. Solution 2, less ideal but common in quick fixes. Grant others write permission, use with caution. Sudo chmod o+ w var/log/mywebapp. Or sudo chmod 757 var/log/mywebapp. This grants write permission to everyone on the system for this directory. Generally avoided in production if more precise methods are possible. Best practice: principle of least privilege. Always grant only the necessary permissions. Avoid using chmod 777, read, write, execute for everyone, unless absolutely forced to and you understand the security implications. It opens up your system to potential unauthorized modifications. Understanding and correctly configuring file and directory permissions is a critical skill. It impacts system security, integrity, and the smooth operation of applications. Practice these concepts, and you'll find yourself much more capable in diagnosing and resolving Linux system issues. Summary and key takeaways. The Linux file system is a single, unified hierarchy starting from, defined by the File System Hierarchy Standard, FHS. Key directories like etc., configurations, /var/log logs, home user data, and /usr/bin executables have specific purposes. Absolute paths start from, while relative paths are based on your current directory, for current, for parent. Linux differentiates between file types: regular files, directories D, symbolic links L, and various device files. Permissions control who can read R, write W, or execute X, a file or directory. They are set for the owner, group, and others. Write permission on a directory is needed to create, delete, or rename files within it. Execute permission on a directory is needed to enter it or access its contents. Use chmod to change permissions, either using symbolic mode e.g., U plus X, go W, or octal numeric mode e.g., 755, 644. Use chown to change the user and or group owner, and chgrp to change only the group owner. These often require sudo. Special permissions like suid, sgid, and the sticky bit add advanced functionality, but require careful consideration due to security implications. Permission denied, errors are common. Troubleshooting involves checking the user service attempting access, and then confirming the RWX permissions and ownership for all relevant files and parent directories. Follow the principle of least privilege, grant only the minimum necessary permissions. Practical exercise, navigate and explore, go to your home directory. Run lsf to see your direct subdirectories. Run tree, you might need to install it. Sudo apt install tree or sudo dnf install tree to see a more detailed hierarchy of your home directory. Navigate to etc. and list its contents with LSL. Observe the various file types and permissions. Pay attention to root ownership. Navigate to var/log/ and list its contents with LSL. Identify typical log files like syslog or others. Practice permissions. In your home directory, create a new directory, test permissions. Create 2 files inside it, secretnote.txt and myupscript.sh. Check their initial permissions with LSL test permissions. Scenario 1. Secretnote.txt. Make secretnote.txt readable and writable only by you, the owner, and no one else. Hint, chmod octal. Confirm with LSL. Scenario 2. myupscript.sh. Make myupscript.sh executable for you, the owner, and readable executable for others in your group, but not writable by anyone else. Hint, chmod octal or symbolic. Confirm with LSL. Scenario 3. Test permissions directory. Make test permissions private so only you can enter, cd, and list its contents. Hint, chmod octal. Confirm with LSLD. Simulate a permission denied error. Can you, as sysadmin, copy a file into root, e.g. cp dummy.txt root? Why or why not? Look at LSLD root permissions. Ownership requires sudo. Create a dummy group, sudo group add mydevs. Change the group ownership of test permissions to mydevs. Hint, chgrp. Confirm with LSLD. Change the user owner of secretnote.txt to root and the group owner to mydevs. Hint, chown. Confirm with LSL test permissions /secretnote.txt. Remove the dummy group, sudo groupdel mydevs. Self-reflection. Did you run into permission denied errors? That's expected and good practice. How did you diagnose them using LSL and the principles explained? Chapter 5. Users, Groups, and Security. Managing Identity and Access. In the previous chapter, we explored the Linux file system and the critical role of permissions in controlling access to files and directories. Building on that foundation, this chapter delves into how Linux identifies who is accessing the system and how those individuals or services are organized to manage access. Through users and groups. Mastering user and group management is fundamental to maintaining a secure, organized, and collaborative Linux environment. 5.1 Users and Groups. The foundation of identity and access control. Linux is a multi-user operating system, meaning multiple people can have accounts and interact with the same system simultaneously, either directly or remotely. To manage these individuals and control what they can do, Linux relies on the concepts of users and groups. Users. Every person or service that interacts with a Linux system has a user account. This account uniquely identifies them to the system. Each user has a unique username, e.g. sysadmin, John Doe, www.data, a unique user ID, UID, which is a numerical identifier. The system internally prefers UIDs over usernames. A home directory, e.g. home John Doe, where they store personal files. A login shell, e.g. bin bash, which defines the command line interpreter used when they log in. A password for human users, providing authentication. Groups. A group is simply a collection of user accounts. Groups simplify permission management. Instead of assigning permissions to individual users repeatedly, you assign permissions to a group and then add relevant users to that group. This is a powerful concept for managing access to shared resources. Each group has a unique group ID, GID, a numerical identifier. Every user belongs to at least one primary group. When a user creates a new file or directory, its group ownership is typically set to the user's primary group. Users can also belong to multiple supplementary or secondary groups, granting them additional access permissions associated with those groups. The principle of least privilege. A core security principle in system administration is to grant users and services only the minimum necessary permissions to perform their functions, and no more. This limits the potential damage if an account is compromised. Understanding users and groups is crucial for implementing this principle effectively. 5.2. Identifying yourself and others. Who. Before you manage users, it's helpful to know how to identify who you are and who else is on the system. Who am I? This command simply tells you the effective username of the current user. Type who am I. Expected output, sysadmin or your current username. Who, this command shows who is currently logged into the system. Type who. Expected output, example. Sysadmin TTY 1 2023 to 4 to 23 830. 192.168.1.100. This shows the username, the terminal they are using, e.g., physical console TTY1 or a remote connection, the login time, and possibly their IP address. This command provides much more detailed information about your user and group memberships. Type id. Expected output example. UID equals 1000 sysadmin, GID equals 1000 sysadmin, groups equals 1000 sysadmin, 4 atom, 24 cdrom, 27 sudo, 30 dip, 46 plugdev, 110 lxd. UID. Your user ID, 1000, is common for the first non-root user. GID. Your primary group ID, often the same as your UID. Groups. A comma-separated list of all groups you belong to, including your primary group. This is critical for troubleshooting access issues. 5.3 Key system, files for users and groups. Information about users and groups is stored in specific plaintext files. As root or with sudo, you can inspect these files, but generally, you should use commands like userad, usermod, etc. to modify them, as these commands ensure the files are updated correctly and consistently. etc/password. This file contains a list of all user accounts on the system. Each line represents one user and has 7 colon-separated fields. Username. Password field X. An X indicates that the actual encrypted password is stored in etc. shadow. UID, user ID. GID, primary group ID. GECOS field, user information. Full name, office location, contact info optional. Home directory path. Login shell path. Example line from /etc/password. Sysadmin x10.0.10.0 system administrator /home/sysadmin /bin/bash. Root x00 root/bin bash. The root user always has UID 0. etc. shadow. This file stores encrypted user passwords and password aging information. It's highly restricted, only the root user can read it. For security, never manually edit this file. Each line corresponds to a user in etc/password. The second field contains the encrypted password hash. etc. group. This file lists all groups on the system. Each line represents one group and has 4 colon-separated fields. Group name. Password field X. If there's an X here, it means the group can have a password for GID access, stored in /etc/gshadow, rarely used. GID, group ID. Group members, a comma-separated list of supplementary members of this group. Example line from etc. group, sysadmin x 1000. This group's only member is its primary user via UID mapping. Sudo x 27. Sysadmin, the sudo group has sysadmin as a member. MyTeam x 1001. John, Jane, a custom group MyTeam with members John and Jane. etc/gshadow. Stores encrypted group passwords, if any, and group administrator information. Also highly restricted. 5.4 Managing user accounts. You'll use several commands to create, modify, and delete user accounts. Remember, these actions require root privileges, so you'll preface them with sudo. Userad versus educer. Userad. This is a low-level command that creates a new user account with default settings. It does not create a home directory or prompt for a password by default. It's often used in scripts. Educer. This is a friendly, interactive script typically found on Debian/Ubuntu systems, but not on CentOS Red Hat, that simplifies user creation. It prompts for all necessary information, creates the home directory, copies skeleton files, bashrc, etc., and sets up sensible defaults. For manual user creation, a doser is recommended on systems where it's available. Example, creating a new user using a doser, Ubuntu/Debian. Sudo aduser jondo. The system will then prompt you for new password for a new user, type the password. Retype new password, re-enter the password. Full name. Enter the user's full name. Room number, optional. Work phone, optional. Home phone, optional. Other, optional. Is the information correct? Y/N. Press Y for yes. This process will create the user jondo, their home directory home jondo, set their primary group to jondo with GID 1001 or next available, and assign them the default login shell. Example, creating a new user using userad, sent OS Red Hat or for advanced use. Sudo userad create home, shell bin bash jondo. Create home m, creates the home directory for the user. Shell bin bash s, sets the login shell. This command does not set a password, you must set it separately. 5.4.1 Setting and changing passwords. Password. After creating a user with userad, you must set their password. Even after using a doser, you might need to change a user's password. To change a user's password as admin. Sudo password jondo. You'll be prompted to enter the new password twice. To change your own password as a regular user, password no username needed. You'll be prompted for your current password, then the new one twice. 5.4.2 Modifying user accounts. Usermod. The usermod command allows you to change various aspects of an existing user account. Remember, the user should not be logged in when you modify their account with usermod. Change a user's username. Sudo usermod l new surname old surname. L for login name. You'll also likely need to move their home directory manually if you don't use D or SM, or if the new name needs a new home folder. Change a user's primary group. Sudo usermod, GNU group name username. Add a user to a supplementary group. Sudo usermod ag new group name username. A for append, G for supplementary groups. Crucial to use, A so you don't remove them from other groups. Change a user's home directory. Sudo usermod dnew home path, M username. D for home directory, M to actually move contents of old home to new one. Change a user's shell. Sudo usermod /bin/sh username. Lock a user account, prevent login without deleting. Sudo usermod l username. Unlock a user account. Sudo usermod u username. 5.4.3 Deleting user accounts. Userdel. The userdel command removes a user account from the system. Sudo userdel username. This deletes the user, but leaves their home directory and mail spool intact. Sudo userdel remove username, or sudo userdel r username. This deletes the user account and their home directory and mail spool. This is generally preferred for a clean removal. 5.5 Managing groups. Just as with users, you'll manage groups to organize users and access. 5.5.1 Creating groups. Grouped. The grouped command creates a new group. Sudo grouped webdevs creates a group named webdevs with the next available GID. 5.5.2 Modifying groups. Groupmod. The groupmod command allows you to change a group's name or GID. Change a group's name. Sudo groupmod, n new group name old group name. Change a group's GID. Sudo groupmod, gnugid group name. Be cautious changing GIDs, especially for groups with existing files. 5.5.3 Deleting groups. Groupdel. The groupdel command removes a group. Sudo groupdel webdevs. Note, you cannot delete a group if it is the primary group for any existing user. 5.6 The power of sudo, delegated authority. By default, the root user has complete control over the system. For security, you typically do not log in directly as root for day-to-day administration. Instead, you use sudo, short for superuser. Sudo allows authorized users to execute commands with root privileges or other users' privileges. When you use sudo, you are prompted for your own password, not the root password. This adds a layer of accountability, as your actions are recorded in logs, specifically /var/log/auth-log. 5.6.1 The etc/sudoers file. The /etc/sudoers file controls who can use sudo and what commands they can run. This file should never be edited directly with a text editor like Nano or Vim. You must use the visudo command. Sudo visud. Visudo is a special editor that checks the syntax of etc/sudoers before saving. If you make a mistake and save, you could lock yourself or other administrators out of sudo capabilities, which is a major problem on a server. A typical sudoers entry for a user or group looks like this. Username all equals all. This means username first all can run commands from all terminals second all, as all users third all, as all groups fourth all, and can run all commands final all. A common setup for administrative users is to make them members of the sudo group on Ubuntu/Debian or the wheel group on CentOS Red Hat. The sudoers file then has a line enabling this group. %sudo all equals all for Ubuntu/Debian. %wheel all equals all for CentOS Red Hat. The % symbol indicates a group. So, to give Jondo sudo privileges on Ubuntu, sudo usermod ag sudo Jondo. Then, Jondo would need to log out and back in for the group membership change to take effect. 5.7 Practical Applications and Security Best Practices. Dedicated service accounts. For applications like web servers, databases, or mail servers, create dedicated low-privilege user accounts, e.g., www.data, MySQL. These accounts should only have access to the files and resources they absolutely need. Limit sudo access. Don't give sudo access to everyone. Only grant it to users who legitimately need administrative privileges. If a user only needs to run a specific command as root, you can configure granular sudo rules in etc/sudoers to allow only that command. Strong passwords. Enforce strong password policies. Combine uppercase, lowercase, numbers, and symbols. Regularly change passwords. Password aging. Configure password expiration policies. You can change these using change command. Disable unused accounts. Regularly review user accounts and disable or delete those that are no longer needed. Dormant accounts are a security risk. Monitor login attempts. Regularly check var/log/authlog for suspicious login attempts or sudo usage. Primary versus supplementary groups. Use primary groups wisely to define a user's default ownership of new files. Use supplementary groups to grant access to shared resource groups. Directory permissions for collaboration. When multiple users need to collaborate on files within a directory, create a common group for them. Then, set the directory's owner to root or a service user, its group to the common group, set permissions to rwx 770, and apply the sgid bit, chmod g+s directory name, so new files inherit the group ownership. Managing users and groups effectively is a continuous process. It's about balancing the needs for collaboration and access with the critical demands of system security. By following these principles and practicing with the commands, you'll be well equipped to control who does what on your Linux systems. Summary and key takeaways. Users are unique identities with a username, UID, home directory, and shell. Groups are collections of users with a group name and GID, simplifying permission management. The principle of least privilege dictates granting only necessary access. Key user group information files. etc/password, etc shadow, etc group, /etc/g shadow. Whoami, who, and id commands help identify current users and their group memberships. User creation. Aducer, interactive, Debian/Ubuntu, or userad, low-level, universal, requires manual home dir creation and password setting. Password sets changes user passwords. Usermod modifies user attributes, username, home directory, groups, shell, lock-unlock account. Use usermod ag to add to supplementary groups without removing others. Userdel with R to remove home directory, deletes user accounts. Group management. Groupadd to create, groupmod to modify, groupdel to delete groups. Sudo allows authorized users to execute commands with elevated privileges checked against etc/sudoers. Always use vsudo to edit etc/sudoers to prevent syntax errors. Security best practices include creating dedicated service accounts, limiting sudo access, enforcing strong passwords, regularly reviewing accounts, and using group permissions effectively for collaboration. Practical exercise: create a test user and group. Create a new group called developers. Sudo group add developers. Create a new user devuser1. Sudo adducer devuser1, set a password. Add devuser1 to the developers group. Sudo usermod ag developers devuser1. Verify devuser1 group memberships, id devuser1. What are their primary and supplementary groups? Create another user devuser2. Add devuser2 to the developers group as well. Shared project directory. Create a directory called /opt/projectalpha. Sudo mkdir /opt/projectalpha. Change the ownership of /opt/projectalpha so that root is the user owner and developers is the group owner. Sudo chown root developers /opt/projectalpha. Set the permissions on /opt/projectalpha so that the owner root has all permissions RWX. The group developers has read, write, and execute permissions RWX. Others have no permissions. Apply the sgid bit so new files /dires inherit the developers group. Hint: sudo chmod 2770 /opt/projectalpha. Confirm the permissions lsld /opt/projectalpha. Test access. Switch to devuser1. Sudo iu devuser1. This allows you to act as devuser1 without logging out and back in. Try to create a file in /opt/projectalpha. Touch /opt/projectalpha/doc1 txt. Check the owner should be devuser1 and group should be developers of doc1 txt. lsl /opt/projectalpha/doc1 txt. Why did it inherit the developers group? Try to create a file in root. Touch root /myfile.txt. What error do you get? Why? Exit devuser1 shell. Exit. You'll return to your original sysadmin user. Clean up. Delete the test users. Sudo usertl rdevuser1 and sudo usertl rdevuser2. Delete the developers group. Sudo grouptl developers. Remove the project directory. Sudo rm rf/opt/projectalpha. Further reading resources: man userad, man usermod, man passud, man grouped, man groupmod, man vsudo for detailed command options. Linux documentation on file permissions and security. Chapter 6. Processes and Services, Understanding How Linux Works. You've mastered navigation, permissions, and user management. Now it's time to understand the dynamic heart of a Linux system, its processes and services. These are the active programs, tasks, and background operations that make the operating system function and allow it to run applications. As a system administrator, your ability to monitor, manage, and troubleshoot processes and services is paramount to ensuring system stability, performance, and the availability of critical applications. 6.1 What is a process? At its most fundamental level, a process is an instance of a running program. When you type a command and press enter, the shell creates a new process to execute that command. Every command you've executed so far ls, cd, ps, systemctl, has run as a process. Each process on a Linux system is uniquely identified by a process ID, PID. This PID is a numerical identifier assigned sequentially when the process starts. When a process finishes, its PID is released and can be reused by a new process later. Processes don't just run commands. They also manage resources like CPU time, memory, and I/O operations. Understanding the lifecycle and behavior of processes is key to system performance tuning and troubleshooting. 6.2 Process lifecycle and states. Processes don't just magically appear and disappear. They go through various stages or states during their existence. While the exact states can be more granular, here are the most common ones you'll encounter. Running R. The process is currently executing on the CPU or is ready to run. Sleeping S. The process is waiting for an event to occur, e.g., I/O completion, a system call to finish, or a signal. Most processes spend much of their time in a sleeping state, waiting for input or a task to complete before they need CPU time again. Stopped T. The process has been suspended, usually by a signal e.g., Ctrl+Z from the keyboard or a debugging tool. It can be resumed later. Zombie Z. A process that has terminated but whose entry still remains in the process table because its parent process hasn't yet collected its exit status. Zombie processes consume almost no resources, but can indicate a problematic parent process if they accumulate. Uninterruptible sleep D. The process is waiting for an I/O operation to complete and cannot be interrupted. This often indicates a problem with underlying hardware or a very heavy disk operation. Idle I. On some systems, this indicates a kernel thread that is not performing any activity. 6.3 Monitoring processes. Being able to see what processes are running is the first step in managing them. Linux provides several powerful tools for this. 6.3.1 PS. Listing processes. The PS command, short for process status, displays information about current processes. It's often used with options to get the most useful output. PSOX. This is one of the most common combinations. Show processes for all users. U. Display user and owner information. X. Show processes not attached to a terminal daemon processes. Type PSOX and press enter. Output will typically include columns like user, the user owning the process, PID, the unique process ID, %CPU, the percentage of CPU time the process is currently using, %MEM, the percentage of physical memory the process is using, VSC, virtual memory size in kilobytes, RSS, resident set size physical memory used in kilobytes, TTY, the terminal from which the process was started, or, for daemons, stat, the current state of the process, e.g., S for sleeping, R for running, SS for sleeping session leader, plus for foreground process group. Start, the time the process started. Time, total CPU time consumed. Command, the command that started the process, often with its arguments. The output can be very long. You'll often combine PSOX with grep to filter for specific processes. PSOX grep SSH. This will show all processes related to SSH. PSF, another popular combination, similar to PSOX but uses different output formatting and selects processes differently. PSF shows processes from the current user as well, not just all users. E, select all processes. F, do full format listing, showing parent-child relationships. PSF grep Apache 2 to find Apache web server processes, for example. 6.3.2 Top. Real-time monitoring. While PS gives you a static snapshot, Top provides a dynamic, real-time view of running processes. It updates periodically, showing processes consuming the most resources at the top. Type Top and press Enter. The top section shows summary information: uptime, number of users, load average, total tasks processes, and CPU memory statistics. The lower section lists individual processes, sorted by CPU usage by default. Key commands within Top: Q, quit Top. K, kill a process, you'll be prompted for PID and signal type. M, sort by memory usage. P, sort by CPU usage default. U, filter by user, you'll be prompted for username. Top is invaluable for quickly identifying runaway processes that are consuming excessive CPU or memory. 6.3.3 HTOP, Enhanced Interactive Monitoring. HTOP is an interactive process viewer that offers a more user-friendly interface than Top. It's not usually installed by default, but it's a favorite among administrators. To install HTOP, sudo apt install HTOP, ubuntu/debian, or sudo dnf install HTOP, CentOS Red Hat. Type HTOP and press Enter. It presents a colorful, easy-to-read display with CPU and memory usage graphs at the top. You can use arrow keys to navigate the process list, F keys for common actions, e.g., F3 for search, F9 for kill, F6 for sort. HTOP is often preferred for visual clarity and ease of interaction when monitoring a busy system. 6.4 Managing processes. Once you've identified a process, you might need to stop it, pause it, or change its priority. 6.4.1 Kill family of commands and signals. Linux processes respond to signals, which are software interrupts that can be sent to a process to tell it to do something, e.g., terminate, reload its configuration, pause. The kill command and its relatives are used to send these signals. Kill PID sends a specific signal to a process identified by its PID. Kill, by default, sends SIGTERM signal 15 terminate. This is a polite request to a process to shut down gracefully, allowing it to save data and close files. Kill-9 PID sends SIGKILL, signal 9 kill. This is a forceful, immediate termination that the process cannot ignore. It doesn't allow the process to clean up, so use it with caution, only when SIGTERM doesn't work. Kill PID sends SIGHUP, signal 1 hang-up. This often tells a process, especially a daemon, to reload its configuration files without fully restarting. Example: if you find an unresponsive process with PID 12345, try kill 12345, polite terminate. If it persists after a few seconds, use kill-9 12345, force kill. Kill-all kills processes by name. This is convenient for stopping all instances of a program. Sudo kill-all Apache 2 attempts to gracefully stop all processes named Apache 2. Sudo kill-all -9 Firefox forcefully stops all Firefox browser processes. pkill kills processes by name, but with more advanced pattern matching, similar to grep. pkill-u username kills all processes owned by username. pkill fpattern kills processes where pattern matches the full command line, not just the program name. Important note on sudo: you can only kill processes that you own, or processes if you are the root user, or using sudo. Attempting to kill another user's process without sudo will result in an operation not permitted error. 6.4.2 Backgrounding processes, and nohup and job control. When you run a command directly, it runs in the foreground, meaning your shell prompt is tied up until the command finishes. You can't type new commands. Running in the background, and to run a command and immediately get your prompt back, append an ampersand, and to the command. Sleep 300, and this runs the sleep command in the background for 300 seconds. Nohup. Some commands, if run in the background, will still terminate if your shell session, terminal, closes, e.g., if you log out from SSH. Nohup, no hang-up, prevents this by disassociating the process from your terminal. Nohup mylong running script sh, and the output will be redirected to nohupout by default unless specified. Job control. Within a single shell session, you can manage foreground and background processes using job control. To move a running foreground process to the background, press Ctrl+Z, this stops the process, then type BG and press Enter, this resumes it in the background. To list background jobs, type jobs. Output will show job numbers, e.g. 1, 2. To bring a background job to the foreground, type FG%job number, e.g. FG%1. While useful for quick, interactive tasks, most long-running server processes are managed as services by the init system, which is a more robust and persistent way to handle them. 6.5 What is a service, daemon? A service, often called a daemon from Greek mythology, a supernatural being that works in the background, is a program that runs continuously in the background, typically without direct user interaction. Services provide core functionalities for the operating system or applications. Examples of common Linux services: daemons, web servers, Apache, Apache 2, Nginx, Nginx. Database servers: MySQL, MySQL, PostgreSQL, PostgreSQL. SSH server, SSHD. Network services: DHCP, DNS, NTP. Logging services: rsyslog, journaled. Services are designed to start automatically when the system boots up and remain running until the system shuts down or until they are explicitly stopped or restarted by an administrator. 6.6 The init system, systemed. For many years, Linux distributions used various init systems to manage services during boot-up and runtime, traditionally sysvinit, later upstart. Today, the overwhelming majority of modern Linux distributions, including Ubuntu, CentOS, Red Hat, Fedora, Debian, use systemed as their primary init system. Systemed is a powerful and complex system for managing processes, services, and other system components. It handles almost everything after the kernel loads, including mounting file systems, starting networking, and launching all the various services. 6.6.1 Systemtool, the primary tool for service management. The systemtool command is your main interface for interacting with systemed and managing services. Checking service status. Systemtal status SSHD. Check the status of the SSH daemon. Output will show if it's active running, inactive dead, enabled starts on boot, disabled its PID, recent log entries, etc. Press Q to exit the status view. Starting a service. Sudo systemtal start Apache 2 starts the Apache web server service if it's installed and configured. Stopping a service. Sudo systemtal stop SSHD stops the SSH daemon. Be careful not to lock yourself out remotely. Restarting a service. Sudo systemtal restart nginx stops and then starts the nginx web server. This is useful after changing configuration files. Reloading a service, if supported. Sudo systemtal reload Apache 2. Some services can reload their configuration without a full restart, minimizing downtime. Use restart if reload isn't supported or effective. Enabling a service, start on boot. Sudo systemtal enable Apache 2 configures Apache to start automatically every time the system boots. This creates a symbolic link in the appropriate system directory. Disabling a service, do not start on boot. Sudo systemtal disable FTP prevents the FTP server from starting automatically on boot. Listing services, units. Systemtal list units type equals service, lists all system service units and their status. Systemtal list unit files type equals service, lists all service unit files and whether they are enabled or disabled. 6.6.2 Unit files. System services are defined by unit files, which are plain text configuration files typically located in etc. system or lib system. These files describe how a service should be started, stopped, its dependencies, its environment, and so on. As an administrator, you might occasionally need to inspect or modify these files, but typically you'll use systemtal for management. 6.7 The Linux boot process, high level. To fully grasp services, it's helpful to understand their place in the Linux boot process. BIOS UEFI initialization. When you power on a computer, the basic input-output system, BIOS or Unified Extensible Firmware Interface, UEFI, performs initial hardware checks and hands over control to the boot device. Bootloader, grub. The bootloader, most commonly grub, Gerand Unified Bootloader, loads the Linux kernel into memory. Grub also allows you to choose which operating system or kernel version to boot. Kernel initialization. The Linux kernel loads, initializes hardware, and performs self-tests. Init system, systemed. The kernel then starts the first process, which is the init system, PID1, typically systemed. Service startup. System takes over, reading its configuration, unit files, mounts file systems, sets up networking, and starts all the configured services, daemons, in the correct order based on their dependencies. Login prompt. Once core services are running, the system presents a login prompt or a graphical desktop if configured, ready for user interaction. 6.8 Practical applications and troubleshooting. Effective process and service management is central to your role as a Linux administrator. Identifying runaway processes. If your server is slow, check top or htop immediately. Look for processes consuming high % CPU or %MEM. If it's an application process, consider restarting its service. If it's an unexpected process, research it and consider terminating it if it's malicious or problematic. Restarting services after configuration changes. Whenever you modify a service's configuration file, e.g., Apache's httpd.conf, you almost always need to restart or reload the service for the changes to take effect. Sudo systemtal restart service name. Ensuring services start on boot. Always remember to use sudo systemtal enable service name for any service that needs to be available after a system reboot. If an important service isn't working after a reboot, systemtal status and checking if it's enabled should be your first steps. Debugging failed services. If a service fails to start or an application isn't working, check its status. Systemtal status service name. This often shows the most recent error message. Check the system journal for more detailed logs. Sudo journalctl zu service name. The Z option shows the most recent logs and provides additional context, and U service name filters by specific unit. Inspect the service's own log files, typically found in var/log/. The journoctal command. Systemd uses a centralized logging system called the journal. Journoctal is the command line utility to query and display messages from the journal. Journoctal shows all system logs, can be very long. Journoctal F follows log output in real time, like tailf. Journoctal U service name shows logs for a specific systemd unit service. Journoctal S yesterday shows logs since yesterday. Journoctal PR shows only error messages. Understanding processes and services is crucial for maintaining a healthy and responsive Linux system. Whether an application is misbehaving or the system feels sluggish, knowing how to inspect, manage, and debug these core components will be your daily bread and butter as a Linux administrator. Summary and key takeaways. A process is a running instance of a program uniquely identified by a PID. Processes have various states: running, sleeping, stopped, zombie. Use PSOX or PSF for a static snapshot of processes. Pipe the output to grep to filter. Use top or htop for real-time, interactive monitoring of processes and system resources. The kill command sends signals to processes to terminate them. SIGTERM 15 graceful, SIGKILL 9 forceful. Killall and pkill kill by name. Commands can be run in the background using and nohup prevents termination on logout. Jobs FG BG manage interactive job control. A service, or daemon, is a program that runs continuously in the background to provide specific functionality. Systemd is the modern init system used by most Linux distributions for managing services during boot and runtime. The systemtool command is essential for managing services. Status service name, start service name, stop service name, restart service name, enable service name, configure to start on boot, disable service name, configure not to start on boot. List units type equals service. The Linux boot process progresses from BIOS UEFI to bootloader grub, then the kernel, then systemd PID1, and finally, systemd starts all configured services. Troubleshooting involves checking service status, systemtool status, inspecting logs journoctal, and identifying resource-consuming processes top/htop. Practical exercise. Explore processes. Run PSOX and scroll through the output. Try to identify processes you recognize, e.g., SSHD your shell. Run top. Observe the CPU and memory usage. Press M to sort by memory, then P to sort by CPU. Press Q to quit. Install htop if you don't have it and play with its interactive features. Manage a dummy process. Open a new terminal or SSH session to your VM. In the new session, run sleep 600. This process will sit there for 10 minutes. Go back to your original terminal session. Use PSOX grep sleep to find the PID of the sleep process. Use kill to gracefully terminate the sleep process, kill PI doff sleep. Verify it's gone with PSOX grep sleep. Manage a service. Check the status of the SSH daemon, systemtool status SSHD. Observe if it's active and enabled. Caution: if you are connected via SSH, stopping SSHD will disconnect you. Be ready to use the VirtualBox console or have another SSH session open. Temporarily disable SSHD from starting on boot. Sudo systemtool disable SSHD. Re-enable it. Sudo systemtool enable SSHD. Restart the SSH daemon. Sudo systemtool restart SSHD. You might notice a brief disconnection if you did this from your current SSH session. Check the recent logs for SSHD. Sudo journoctal u SSHD N20 shows last 20 lines. Simulate a hanging service. If you have a web server installed, e.g., Apache 2 or Nginx, try to start it and then stop it. Sudo systemtool start Apache 2. Sudo systemtool status Apache 2. Sudo systemtool stop Apache 2. If it hangs during stop, you might resort to sudo killall -9 Apache 2 as a last resort, and then sudo systemtool restart Apache 2 to clean up and restart. This is for understanding, usually services restart cleanly. Further reading resources: man ps, man top, man htop, man kill, man systemtool, man journoctal for detailed option explanations. System documentation, though it can be quite technical. Online guides on Linux process and service management. Chapter 7, Networking essentials, connecting your Linux system. In today's interconnected world, a Linux server without networking capabilities is like a powerful supercomputer trapped in isolation. Whether it's serving websites, hosting databases, or providing remote access, your Linux system needs to communicate with other devices. This chapter will demystify the fundamentals of Linux networking, guiding you through core concepts, essential configuration files, and vital command line tools for managing network connections and basic firewall rules. 7.1 Networking Fundamentals, the building blocks. Before we dive into configuration, let's understand some crucial networking concepts that underpin how devices communicate. IP addresses. An Internet Protocol, IP, address is a unique numerical label assigned to each device connected to a computer network that uses the Internet Protocol for communication. Think of it as a street address for your computer on the network. IP4, the most common form, consisting of 4 sets of numbers separated by dots, e.g., 192.168.1.100. IP6, the newer, much larger address space, written as 8 groups of 4 hexadecimal digits, e.g., 2001, 0db8, 85a3, 0000. AE 707334. We'll focus on IP4 for many examples, but the principles generally apply. Subnet mask. Used in conjunction with an IP address, the subnet mask, e.g., 255.255.255.0 or 24 in CIDR notation, defines which part of an IP address refers to the network and which part refers to the host within that network. It helps devices determine if a destination IP address is on the local network or needs to be routed elsewhere. Default gateway. Also known as a router, the default gateway is the device that directs traffic from your local network to other networks, like the Internet. Your Linux system needs to know which device to send data to if the destination is outside its local subnet. DNS, Domain Name System, servers. Computers communicate using IP addresses, but humans prefer easy-to-remember domain names, like google.com. DNS servers act like phone books, translating these human-readable domain names into numerical IP addresses. Your Linux system needs to know where to find these DNS servers. Ports. When data arrives at an IP address, the system needs to know which application or service the data is intended for. This is where ports come in. A port is a number assigned to a specific service. For example, web traffic, HTTP, typically uses port 80, secure web traffic, HTTPS, uses port 443, and SSH uses port 22. Protocols. Protocols are sets of rules that govern how data is formatted and transmitted. Common examples include TCP, Transmission Control Protocol, provides reliable, ordered, and error-checked delivery of data, used for web browsing, email, and file transfers. UDP, User Datagram Protocol, a faster, connectionless protocol that doesn't guarantee delivery, used for services like DNS lookups and online gaming where speed is prioritized over guaranteed delivery. 7.2 Network Configuration Approaches. Linux offers different ways to configure network interfaces, depending on the distribution and desired setup. Modern systems are increasingly relying on tools like NetPlin or Network Manager for abstracting the underlying configuration. Dynamic IP Configuration, DHCP. DHCP, Dynamic Host Configuration Protocol, servers automatically assign IP addresses, subnet masks, gateways, and DNS server information to devices on a network. This is the default and simplest method for most client devices and virtual machines. In your VM, your Linux system likely obtained its IP address via DHCP during installation. Static IP configuration. For servers, it's often preferable to assign a static IP address so its address never changes. This is crucial for services like web servers, DNS servers, or application servers, where clients need a consistent address to connect to. Static configuration requires you to manually specify the IP address, subnet mask, gateway, and DNS servers. 7.3 Essential Networking Commands and Tools. You'll spend a lot of time troubleshooting and verifying network connectivity. These commands are your daily bread and butter. 7.3.1 IP, the modern network configuration tool. The IP command is the modern, powerful, and versatile tool for configuring and displaying network devices and routes. It has largely replaced older tools like ifconfig and root. Display IP addresses, IP or IP adder show. This shows all network interfaces on your system, e.g., low for loopback, ETH0 or EMP03 for your main network interface. Look for the inet line with your IP address. Display routing table, IPR or IP route show. This shows how your system knows where to send network traffic. Look for the default via entry, which indicates your default gateway. Display network link information, IPL or IP link show. Provides information about network interface states, UPDOWN, MAC addresses, and packet statistics. Bring an interface up-down requires sudo. Sudo IP link, set EMP03 up. Sudo IP link, set EMP03 down. Replace EMP03 with your actual network interface name. 7.3.2 Ping. Basic connectivity test. The ping command sends small data packets to a specified host and waits for a response. It's used to test basic network connectivity and measure round-trip time. Test connectivity to a website. Ping google.com. It will continuously send packets. Press Ctrl+C to stop. Test connectivity to an IP address. Ping 8.8.8.8, Google's public DNS server. Interpret output. Bytes from IPADDRSS. Indicates a successful connection and response. Destination host unreachable. No route to the host or device is off. Request timed out. Host is not responding within the timeout period, might be blocked by firewall or simply busy down. 7.3.3 Traceroute, trace path on some distros. Tracing network paths. Traceroute tracks the path that packets take to reach a destination, showing each intermediate router, hop, along the way. This is invaluable for diagnosing where network latency or packet loss might be occurring. Traceroute google.com. The output lists each router's IP address and the time taken for packets to reach that hop. Timeout indicates a hop that didn't respond or is blocked. 7.3.4 Netstat and SS, network connections and listening ports. These commands show current network connections, routing tables, and listening ports, services waiting for connections. SS is newer and generally faster than Netstat. List all listening ports. Sudo SS toln or sudo netstat toln. T, TCP connections. U, UDP connections. L, listening sockets, programs waiting for connections. N, show numerical addresses. Don't try to resolve hostnames/service names. List all active connections, both listening and established. Sudo SS ANP or sudo netstat ANP. A, all sockets. N, numerical addresses. T, TCP connections. P, show process name PID that owns the socket, requires sudo. This output helps you confirm if a service is actually listening on the expected port, e.g., SSH on port 22, HTTP on port 80. 7.3.5 Dig and ENS lookup, DNS lookup tools. These tools are essential for troubleshooting DNS resolution issues. Dig, domain information groper, modern and comprehensive DNS lookup tool. Dig google.com. The answer section will show the IP addresses associated with google.com. You can specify a particular DNS server to query. Dig at 8.8.8.8 example.com. ENS lookup, name server lookup. Older tool but still widely used. ENS lookup google.com. If ping google.com fails, but ping 8.8.8.8 succeeds, it points to a DNS issue on your system. Use dig or ENS lookup to troubleshoot. 7.4 Managing network configuration files. The exact location and format of network configuration files vary significantly between distributions. 7.4.1 Debian/Ubuntu. Netplan. Modern Debian and Ubuntu systems use Netplan for network configuration. Netplan uses YAML files, human-readable data serialization format, to describe the network configuration for all interfaces, and then it generates the configuration for the underlying rendering tool, e.g., Network Manager or System Networked, Configuration Directory, etc. /netplan/. Example, static IP for EMP03. sudo nano etc /netplin /01nec YAML or a similar YAML file. Network version 2. Renderer networked. Ethernets EMP03 DHCP4 no. Addresses 192.168.1.10/24. Routes to a default via 192.168.1.1. Name servers, addresses 8.8.8.8, 8.8.4.4, 192.168.1.1. Optional, true hash prevents system from waiting for this interface. Explanation, version 2 specifies the netplin YAML version. Renderer, networked, indicates that system networked will be used to apply the configuration. Ethernets. EMP03 defines settings for the EMP03 interface. Replace with your interface name. DHCP4. No, disables DHCP for IP4. Use yes for dynamic IP. Addresses. A list of static IP addresses and their CIDR prefixes. Routes defines routing rules, including the default gateway via name servers, addresses, a list of DNS server IP addresses. Apply netplin configuration. Sudo netplin generate generates the backend configuration files. Sudo netplin apply applies the configuration. If you encounter issues, sudo netplin try allows you to test the configuration for 2 minutes and reverts if you don't confirm. 7.4.2 CentOS Red Hat Network Manager. Red Hat-based systems like CentOS and Fedora primarily use Network Manager to manage network connections. Network Manager has configuration files, but the preferred way to interact with it is using the nmcli Network Manager command line interface tool. Configuration directory, etc. /sysconfig /network scripts / for older configurations, or etc. Network Manager system connections for connection profiles. Example, nmcli for static IP. First, identify your connection name, often wired connection 1 or EMP03. nmcli show. Set static IP. Sudo nmcli connection modify, wired connection 1, IP4. Method manual IP4. Addresses 192.168.1.10/24 IP4. Gateway 192.168.1.1 IP4. DNS 8.8.8.88.8.4.4. Bring the connection up or restart it. Sudo nmcli connection up, wired connection 1. For DHCP, sudo nmcli connection modify, wired connection 1 IP4. Method auth. Sudo nmcli connection up, wired connection 1. 7.4.3 DNS resolver configuration / etc. / resolve.conf. Regardless of the distribution, the / etc. / resolve.conf file specifies the DNS servers that your system will use for name resolution. While modern tools like netplin or Network Manager usually manage this file dynamically, you might occasionally need to inspect it or manually edit it for temporary testing. Example etc. / resolve.conf. Nameserver 8.8.8.8. Nameserver 8.8.4.4. Each nameserver line indicates a DNS server IP address. They are tried in order. 7.5 Basic Firewall Configuration. A firewall is a network security system that monitors and controls incoming and outgoing network traffic based on predetermined security rules. Without a firewall, your server is completely exposed to the entire internet. Linux systems typically use NetFilter, a framework within the kernel, to implement firewall rules. User-friendly interfaces are then built on top of NetFilter to manage these rules. 7.5.1 Uncomplicated Firewall, UFW, Ubuntu/Debian. UFW is a very easy-to-use firewall that simplifies iptable's commands. It's often the default on Ubuntu. Check status. Sudo ufwa status verbose shows enabled, disabled, and rules. Enable disable UFW requires sudo. Be careful if connecting remotely. Sudo ufwa enable. Sudo ufwa disable. Default policies. Sudo ufwa default deny incoming, block all incoming connections by default. Sudo ufwa default allow all outgoing connections. Allow specific port services, requires sudo. Allow SSH, port 22. Sudo ufware allow SSH, UFW knows common service names. Sudo ufware allow 22/TCP, explicitly by port and protocol. Allow HTTP, port 80. Sudo ufware allow HTTP. Allow HTTPS, port 443. Sudo ufware allow HTTPS. Allow from a specific IP address. Sudo ufware allow from 192.168.1.50 to any port SSH. Allow SSH only from 192.168.1.50. Delete a rule. Sudo ufware delete allow 22/TCP. Delete by rule or number. Sudo ufware status numbered to see rules with numbers, then sudo ufware delete number. Reset UFW, delete all rules. Sudo ufware reset, this disables UFW and deletes all rules. Use with caution. 7.5.2 Firewalled sent OS Red Hat. Firewalled is the default dynamic firewall management tool on CentOS OS Red Hat. It uses zones, e.g., public, home, internal, to apply different sets of rules depending on the network environment. Check status. Sudo firewall cmd state, running or not running. Get active zones and interfaces. Sudo firewall cmd get active zones. List all open port services in active zone, e.g., public. Sudo firewall cmd list, all zone equals public. Default zone. You will generally be working in the public zone for servers connected to the internet. Allow services, requires sudo. Allow SSH. Sudo firewall cmd add service equals SSH permanent, adds permanently. Allow HTTP. Sudo firewall cmd add service equals HTTP permanent. Allow HTTPS. Sudo firewall cmd add service equals HTTPS permanent. Allow a specific port, e.g., 8080/TCP. Sudo firewall cmd add port equals 8080/TCP permanent. Allow from a specific IP address/subnet. Sudo firewall cmd add rich rule equals rule family equals IP4 source address equals 192.168.1.0/24. Service name equals SSH. Accept permanent. Reload firewall after changes. Sudo firewall cmd reload applies permanent changes. Remove a service port. Sudo firewall cmd remove service equals HTTP permanent. Sudo firewall cmd remove port equals 8080/TCP permanent. Remember, always ensure SSH access is allowed through your firewall before enabling it, especially on a remote server. Otherwise, you'll lock yourself out. 7.6 Practical applications and network troubleshooting. Network issues are among the most common and frustrating problems for system administrators. Here's a systematic approach to troubleshooting. Check physical connection. Is the network cable plugged in? For physical servers. For VMS, is the network adapter correctly configured in VirtualBox, e.g., NAT, bridged? Verify interface status. Use IP or IPL inside the Linux system. Is the interface listed and showing UP, broadcast, running multicast? If not, sudo IP link set emp03 up. Check IP address configuration. Does the interface have an IP address? Is it in the correct subnet? Is the subnet mask correct? Use IP test local network connectivity. Ping another device on the same local network, e.g., your default gateway IP if you know it. If this fails, the problem is local. Check gateway router. Use IPR to verify the default gateway is set. Can you ping your gateway? If not, your system can't reach outside its local network. Test external connectivity, IP address, ping 8.8.8.8. If this works, your system can reach the internet by IP address. If not, the problem is likely with your gateway or upstream connectivity. Test DNS resolution. If ping 8.8.8.8 works but ping google.com fails, it's a DNS issue. Check /etc/resolve.conf for correct nameserver entries. Use diggoogle.com or enslookupgoogle.com to test DNS lookups. Check firewall. Could a firewall, either on your Linux server or an external network firewall, be blocking the connection? Temporarily disable the server's firewall. Sudo ufware disable or sudo systemtool stop firewalled, if safe to do so for testing, and retest. If it works, the firewall was the culprit. Re-enable the firewall and add specific rules. Check SS tone to see if the service you expect to be listening is actually listening on the correct port and interface. Check application service. Is the target application, e.g., web server, database, actually running and configured to listen on the correct port? Use systematically status service name and journalctal, ZU service name. Networking seems complex, but it's built on logical, layered components. With a systematic approach and the tools covered in this chapter, you'll be well equipped to diagnose and resolve most common network connectivity issues. Summary and key takeaways. Networking fundamentals. Understanding IP addresses, subnet masks, default gateways, DNS servers, ports, and protocols, TCP/UDP, is essential. Configuration. Network interfaces can be configured dynamically, DHCP, or statically, manual assignment. Key commands: IP, IPR, IPL, modern tools for displaying and configuring network interfaces and routes. Ping. Test basic host connectivity. Traceroute, tracepath, trace the network path to a destination. SS, netstat, show network connections, listening ports, and associated processes. Dig, enslookup, troubleshoot DNS resolution. Network configuration files, Ubuntu/Debian, etc/netplin/. YAML files are used by netplin. Modify and then sudo netplin apply. CentOS Red Hat. nmcli command line tool is used with Network Manager. Configuration files in /etc/sysconfig/network scripts / or etc. network manager system connections. etc/resolve.conf defines DNS servers. Firewalls, critical for security, controlling network traffic based on rules. Ubuntu/Debian, UFW, sudo ufwa allow SSH, sudo ufwa enable. CentOS Red Hat. Firewalled, sudo firewall cmd add service equals SSH permanent, sudo firewall cmd reload. Always allow SSH before enabling the firewall on a remote server. Troubleshooting network issues. Follow a systematic approach. Physical layer, IP configuration, gateway, DNS, firewall, then application service. Practical exercise. Verify current network info. Run IP and identify your VMS IP address, subnet mask, CIDR, and network interface name, e.g., EMP03. Run IPR and identify your default gateway IP address. Run cat etc/resolve.conf to see your DNS servers. Ping your default gateway, ping gateway IP address. Ping an external IP address, ping 8.8.8.8. Ping an external domain name. Ping google.com. Run dig google.com and enslookup google.com. Test listening services. Run sudo sstoln. Verify that SSHD is listening on port 22/TCP. Optional. If you install a web server, e.g., sudo apt install Apache 2y, restart it, and then run sudo sstoln again. You should see Apache 2 or HTTPD listening on port 80/TCP. Practice firewall rules, UFW or firewalled. Important. Ensure you are comfortable with your VirtualBox console before doing this, in case you lock yourself out. Check your firewall status. Sudo ufwa status verbose or sudo firewall cmd list, all zone equals public. If your firewall is inactive not running, enable default deny for incoming traffic. Sudo ufwa default deny incoming, UFW, or sudo firewall cmd, set default zone equals public and ensure public zone policy is correct, firewalled. Add a rule to allow SSH, UFW. Sudo ufwa allow SSH, then sudo ufwa enable. Firewalled, sudo firewall cmd add service equals SSH permanent, then sudo firewall cmd reload. Verify you can still SSH into your VM from your host. If your firewall is active running, try to break something temporarily. Disable one of your existing firewall rules, e.g., SSH if you're brave and on the console. See if it cuts off connections. Re-add the necessary rules. Observe how the SSH connection is affected by firewall rules that include or exclude SSH. Further reading resources. Man IP, man ping, man traceroute, man SS, man dig, man enslookup, man ufwa, man firewall cmd for comprehensive details. Systemed networked documentation for netplin deep dive man system networked. Network manager documentation, man nmcli. General networking tutorials, e.g., TCP/IP explained, subnetting basics. Chapter 8, Software Management, Tools of the Trade for Packages and Updates. In the previous chapters, you've learned to navigate your Linux system, manage users and their permissions, and configure networking. Now, it's time to populate your server with the applications and tools it needs to perform its functions. This chapter focuses on software management, the process of installing, updating, removing, and maintaining software packages on your Linux system. Understanding package managers is arguably the most crucial skill for keeping your server secure, stable, and up-to-date. 8.1 The Linux Software Landscape. How do you get software onto a Linux system? There are generally two primary methods. Compiling from source. This involves downloading the raw source code of a program, then using compilers, like GCC, to translate that code into an executable binary specific to your system's architecture. This offers maximum flexibility, but is complex and rarely used for standard server software. Package management systems. This is the overwhelmingly dominant and preferred method. A package is an archive file containing the compiled software, along with metadata about the program, like its version, description, dependencies it needs to run, and instructions on where to install its files. 8.2 What is a package manager? A package manager is a collection of software tools that automate the process of installing, uninstalling, upgrading, and configuring software packages on an operating system. It's the central hub for managing software on your Linux system. 8.2.1 Benefits of package managers. Dependency resolution. Software often relies on other software, libraries, utilities to function. These are called dependencies. Package managers automatically identify and install all required dependencies, preventing missing file errors and ensuring programs run correctly. Centralized updates. Instead of manually checking each application for updates, the package manager can update all installed software on your system with a single command. This is vital for security and stability. Consistency and reliability. Packages are usually pre-compiled, tested, and configured for your distribution, leading to more reliable installations. Easy removal. Package managers track all files installed as part of a package, making it easy to completely remove software without leaving behind scattered files. Security. Distributions vet packages for security vulnerabilities before making them available in their repositories. 8.2.2 Repositories. The software store. Package managers fetch software from repositories. A repository is a server that stores a collection of software packages, along with their metadata. Distributions maintain their own official repositories, and you can add third-party repositories for additional software. When you run an update command, your system checks its configured repositories for newer versions of installed packages. When you install a new package, the package manager downloads it from the configured repositories. The two major families of Linux distributions use different package management systems. Debian and Ubuntu and their derivatives use the apt Advanced Package Tool system, which manages deb package files. Red Hat, CentOS, and Fedora and their derivatives primarily use DNF dandified yum or the older yum system, which manage RPM package files. While the underlying commands differ, their functionality is largely similar. 8.3 apt. Debian and Ubuntu's package management system. apt is a powerful command line tool for managing deb packages. It works with a cache of available packages and information about them. 8.3.1 Updating the package cache, apt update. The first command you should run after connecting to a new Ubuntu/Debian system, and regularly thereafter, is apt update. This command downloads the freshest package lists from the repositories and updates app's local cache of available packages. It does not actually install or upgrade any software. Sudo apt update. 8.3.2 Upgrading installed packages, apt upgrade and apt full upgrade. Once your package cache is up to date, you can upgrade your installed software. Apt upgrade. This command upgrades all installed packages to their latest versions, but it will not remove any existing packages or install new ones to satisfy new dependencies. It only performs safe upgrades. Sudo apt upgrade. You will be prompted to confirm the upgrade, YN. apt full upgrade. This command performs a more comprehensive upgrade. It will install new packages and remove existing ones if necessary to resolve dependency changes. Use this, for example, when upgrading between distribution versions or after major system changes. Sudo apt full upgrade, use with caution in production, know what it's upgrading. 8.3.3 Installing new packages, apt install. To install a new software package, sudo apt install package name. Replace package name with the actual name of the software, e.g., Nginx, MariaDB Server, Vim. apt will automatically find and install all necessary dependencies. You can install multiple packages at once. Sudo apt install Nginx php-fpm ImageMagick. 8.3.4 Removing packages, apt remove and apt purge. To remove installed software, apt remove package name. This command uninstalls the specified package, but retains its configuration files. This is useful if you might reinstall the package later and want to keep your settings. Sudo apt remove nginx. apt purge package name. This command totally uninstalls the specified package, including its configuration files. This is generally preferred for a clean removal. Sudo apt purge nginx. 8.3.5 Removing unused dependencies, apt auto remove. Sometimes, when you install new software, it pulls in many dependencies. When you remove that software, some of those dependencies might no longer be needed by any other installed package. Sudo apt auto remove. This command automatically removes those no longer needed dependency packages, freeing up disk space. It's good practice to run this periodically. 8.3.6 Searching for packages, apt search, apt show. apt search keyword helps you find packages by searching package names and descriptions. apt search web server. This will list many web server related packages. apt show package name displays detailed information about a specific package, including its version, dependencies, installation size, and description. apt show nginx. 8.4 DNF Yum. Red Hat and CentOS package management system. DNF, Dandified Yum, is the next-generation package manager for RPM-based distributions like Red Hat, Fedora, and CentOS. Since CentOS 8 Stream, it's more performant and has better dependency resolution than the older Yum. While Yum commands still often work as aliases to DNF, it's best to learn DNF. 8.4.1 Updating the system, DNF update. Unlike apt, DNFS update command and YumS update performs both refreshing the cache and upgrading installed packages in one step. Sudo DNF update. This command will identify all available updates and prompt you for confirmation, YN. 8.4.2 Installing new packages, DNF install. To install a new software package, sudo DNF install package name. Replace package name with the actual name of the software, e.g., HTTPD, MariaDB Server, Vim. DNF will automatically resolve and install all dependencies. Sudo DNF install HTTPD PHP MariaDB Server. 8.4.3 Removing packages, DNF remove. To remove installed software, sudo DNF remove package name. This removes the package and its unneeded dependencies. It generally also removes configuration files by default unless explicitly told not to. Sudo DNF remove HTTPD. 8.4.4 Removing unused dependencies, DNF auto remove. Similar to apt, DNF also has an auto remove function to clean up orphan dependencies. Sudo DNF auto remove. 8.4.5 Searching and getting information, DNF search, DNF info. DNF search keyword searches for packages by name and description. DNF search database. DNF info package name displays detailed information about a package. DNF info HTTPD. 8.5 Managing repositories. Both apt and DNF Yum know which repositories to use from specific configuration files. apt repositories. Configured in etc. apt sources list and files within etc. apt sources list D. Each line typically specifies a repository URL, the distribution name, e.g., Focal, Jammy, and components, e.g., main, restricted, universe. To add a new repository, You often add a new line to sources list or create a new file in sources list D using adapt repository command is often the easiest way to add new repositories, especially PPA, Personal Package Archive, repositories. After adding a new repository, always run sudo apt update to refresh the package cache with information from the new repository. DNF yum repositories. Configured in files within etc. yum repos D. These files end with repo and specify repository URLs, GPG keys for authenticity, and whether they are enabled. To add a new repository, you typically download a repo file or create one manually in this directory. For example, for EPEL extra packages for Enterprise Linux, you simply install a release package, sudo dnf install epel release. After adding a new repository, sudo dnf update will automatically pick up the new repository information. Security implication of third-party repositories. Be very cautious when adding third-party repositories. Packages from untrusted sources could potentially contain malicious software or be poorly maintained, leading to system instability or security vulnerabilities. Always verify the trustworthiness of a repository before adding it. 8.6 Software compiling from source, brief overview. While package managers are generally preferred, there are times when compiling from source is necessary. You need the absolute latest version of software not yet packaged. You need specific compilation options or features not enabled in the packaged version. You're developing software and need to test changes. The general steps for compiling most open-source software are download source code. Obtain the source code archive, usually a targz or zip file from the project's website. Extract, unpack the archive. tar xvf software targz. Configure, navigate into the extracted directory and run the configure script. This script checks for system dependencies, identifies your system's specifics, and creates a makefile. Configure. You might need to install development tools and libraries before this step, e.g., Build Essential on Ubuntu, Development Tools Group on CentOS. Compile. Use the make command to compile the source code into executable binaries. Make. Install. Use make install to copy the compiled binaries and other files to their final locations, usually under usr/local/. Sudo make install. Disadvantages of compiling from source. Dependency management. You are responsible for identifying and installing all build and runtime dependencies yourself, which can be complex. No package manager tracking. Software installed from source is not tracked by your system's package manager. This means it won't be automatically updated by apt update/dnf update. You have to manually recompile and reinstall for updates. It's harder to cleanly uninstall as the package manager doesn't know what files belong to it. Time-consuming. Compilation can take a long time for large projects. For these reasons, compiling from source is usually reserved for specific edge cases. 8.7 Key configuration, files related to software. Etc. apt sources list and etc. apt sources list D. Apt repository definitions. Etc. yum repos D. DNF yum repository definitions. Etc. apt preferences D and /etc/dnf/dnf.conf. Control package manager behavior, such as package pinning, preferring certain versions or repositories, or exclusion rules. 8.8 Practical applications and troubleshooting. 8.8.1 Importance of regular updates. Always keep your system updated. This is not just for new features, it's critical for security. New vulnerabilities are discovered daily, and updates often contain patches for these flaws. Regular updates minimize your attack surface. Schedule sudo apt update and in sudo apt upgrade y or sudo dnf update. Y, the Y automatically answers yes to prompts. Use carefully in production, for automatic execution if appropriate, or perform them manually at least weekly. 8.8.2 Package not found. Reason: the package name is misspelled or it's not available in your configured repositories. Solution: double-check spelling. Use apt search or dnf search to find the correct package name. If it's a popular package, ensure you've enabled all standard repositories, e.g., Universe on Ubuntu, Power Tools on CentOS. If it's a niche or very new package, you might need to add a third-party repository or compile from source. 8.8.3 Dependency Issues, Broken Packages. Reason: a package depends on another version of software that conflicts with an already installed package or an upgrade failed midway. Solution: apt, sudo apt fix broken install, attempts to correct a system with broken dependencies. dpkg spath to file or apt hash rdepends package name, used for debugging missing files or understanding dependencies. Solution: DNF. DNF is generally robust at handling dependencies. If issues arise, sudo dnf clean all can clear package caches, and sudo dnf distrosync can attempt to resolve inconsistencies. 8.8.4 Security Implications. Unnecessary software. Only install software that is absolutely needed. Every installed package adds to your system's potential attack surface. Vulnerable versions. Always keep software updated to mitigate against known vulnerabilities. Repository trust. The integrity of your software depends on the trustworthiness of your repositories. Stick to official distribution repositories and well-known, reputable third-party sources. Software management is a continuous administrative task. By mastering the commands for your distribution's package manager and adhering to best practices, you'll ensure your Linux systems remain secure, stable, and ready to perform. Summary and key takeaways. Package management systems are the primary method for installing and maintaining software on Linux, automating dependencies, updates, and removal. Repositories store software packages and their metadata. apt debian/ubuntu commands, sudo apt update, refresh package lists. Sudo apt upgrade, upgrade installed packages safe. Sudo apt full upgrade allowing dependency changes. Sudo apt install package name. Install new software. Sudo apt remove package name, remove package keep config. Sudo apt purge package name, remove package and config. Sudo apt auto remove, remove unused dependencies. apt search apt show. Find and inspect packages. DNF CentOS Red Hat commands. Sudo DNF update, refresh and upgrade. Sudo DNF install package name, install new software. Sudo DNF remove package name, remove package. Sudo DNF auto remove, remove unused dependencies. DNF search DNF info, find and inspect packages. Managing repositories, done via files in etc. apt sources list d, apt, or etc. yum repos d, DNF yum. Be cautious with third-party repositories. Compiling from source, reserved for specific needs, configure make, sudo make install, not managed by package managers. Key security principle. Keep systems regularly updated and only install necessary software to minimize attack surface and patch vulnerabilities. Practical exercise. Exploring your system's software. Run sudo apt update ubuntu or sudo dnf update CentOS. Search for a popular web server. On Ubuntu, apt search engine X. On CentOS, dnf search httpd. Show detailed info for a package. On Ubuntu, apt show engine X. On CentOS, dnf info httpd. Install, configure, and remove using nginx or httpd as example. Install a web server. Ubuntu. Sudo apt install nginxy. CentOS. Sudo dnf install httpdy. Verify installation and service status. Ubuntu. Sudo systemctl status nginx. CentOS. Sudo systemctl status httpd. Enable the web server to start on boot. Ubuntu. Sudo systemctl enable nginx. CentOS. Sudo systemctl enable httpd. Start the web server, if not already running. Ubuntu. Sudo systemctl start nginx. CentOS. Sudo systemctl start httpd. Configure your firewall to allow HTTP, port 80, and HTTPS, port 443. Refer to Chapter 7 if needed. UFW, Ubuntu. Sudo ufware allow HTTP and sudo ufware allow HTTPS. Firewalled CentOS. Sudo firewall cmd add service equals HTTP permanent and sudo firewall cmd add service equals HTTPS permanent, then sudo firewall cmd reload. Test the web server. From your host machine's web browser, navigate to your VMS IP address, e.g., http 192.168.1.10. You should see a default web server page. Remove the web server, Ubuntu, sudo apt purge nginx. CentOS, sudo dnf remove httpdy. Remove unused dependencies. Sudo apt auto remove y or sudo dnf auto remove y. Disable stop the service. Sudo systemctl disable nginx or httpd and sudo systemctl stop nginx or httpd. Remove firewall rules. Refer to Chapter 7. Practice apt/dnf upgrade update and dependency cleanup. Run sudo apt update and in sudo apt upgrade y Ubuntu or sudo dnf update y CentOS. Pay attention to any output. Run sudo apt auto remove or sudo dnf auto remove. Further reading resources. Man apt, man dnf for full command details. Official documentation for your distribution's package manager. Explore apt cache, older apt frontend that provides more detailed info and dpkg, low-level Debian package tool. For CentOS Red Hat, explore module streams with DNF module. Chapter 9, Storage Management, Disks, Partitions, and File Systems. So far, we've explored managing the running processes on your Linux system, configuring its network connections, and installing software. But where does all this data live? The answer lies in storage. Understanding how Linux handles disks, partitions, and file systems is crucial for ensuring data integrity, managing disk space, and preparing your system for growth. As a system administrator, you'll frequently interact with storage, whether adding new hard drives, extending existing partitions, or diagnosing disk space issues. 9.1 Storage devices in Linux. How they're named. When you connect a storage device, like a hard drive, SSD, or USB drive, to a Linux system, the operating system assigns it a device name. These names typically follow a standard convention. SATA IDE drives. Historically, these were named HDA, HDB, etc. for IDE. Modern SATA drives are named SDA, SDB, SDC, and so on. The S stands for SCSI or SATA, and the R, B, C denote the order in which the system detects them. So, SDA is the first drive, SDB is the second, and so forth. NVMe drives. Newer, faster NVMe solid-state drives use a slightly different convention, typically starting with NVMe 0N1, NVMe 0N2, etc. Here, NVMe 0 refers to the controller, and N1 refers to the first device on that controller. Partitions. Individual partitions on a drive are denoted by a number appended to the drive name. For example, SDA1 is the first partition on the first drive, SDA, SDA2 is the second partition, and so on. Virtual disks. In your virtual machine, the single virtual disk is typically named SDA, and its partitions are SDA1, SDA2, etc. You can view a list of recognized block devices, storage devices, using the lsblk list block devices command. lsblk. This command will show a tree-like diagram of your disks and their partitions, along with their sizes and mount points. For example, you might see name MAJ, min RM size RO type MOUNTPONT, SDA8, 0020G0 disk, SDA18, 101M0 part, SDA28, 201023M0 part boot, SDA38, 3018.9G0 part. This output tells us SDA is a 20 GB disk with 3 partitions, SDA1, SDA2, SDA3. SDA2 is mounted at boot, and SDA3 is mounted at the root directory. 9.2 Partitions, dividing your disks. A partition is a logical division of a physical storage device. Instead of using an entire 200 GB hard drive as one continuous block, you can divide it into smaller, more manageable sections. 9.2.1 Why partition? Organization. Separating the operating system from user data or application data can make backups easier and protect critical system files. Multiple operating systems. You can install different operating systems on separate partitions on the same disk. Different file systems. Different partitions can use different file system types, each optimized for a specific purpose. Security stability. Having separate partitions, e.g., for /var/log or /tmp, can prevent a runaway process filling up the entire disk and crashing the system. 9.2.2 Partition Tables, MBR versus GPT. The way a disk's partitions are described is stored in a partition table. The two main types are MBR Master Boot Record, an older standard, limited to 2 TB disk size and usually to 4 primary partitions. It's still common on older systems. GPT GUID Partition Table, the modern standard, supporting very large disks, terabytes and petabytes, and virtually unlimited partitions. It's increasingly common, especially with UEFI-based systems. 9.3 Linux File Systems. Once a partition is created, it needs to be formatted with a file system, also known as making a file system. A file system is the structure that the operating system uses to organize and store files on a storage device. It dictates how data is stored, retrieved, and managed. Without a file system, a partition is just unorganized raw data. 9.3.1 Common Linux File Systems. ext4, fourth extended file system, the current default and most widely used file system for general Linux use. It's a successor to ext2 and ext3, offering increased performance, reliability, and support for larger files and volumes. It includes journaling, which helps rapid recovery after unexpected shutdowns. XFS, a high-performance journaling file system often chosen for servers dealing with very large files and high I/O throughput, e.g., database servers, media servers. It performs well with concurrent operations. BTRFS, B-tree file system, a modern copy-on-write file system with advanced features like snapshots, built-in volume management, checksums for data integrity, and self-healing. It's gaining popularity for its flexibility, but is still considered bleeding edge for some production server use cases. Swap space, not strictly a file system, but a dedicated partition or file used as virtual memory. When your system runs out of physical RAM, it can swap inactive memory pages to this swap space on the disk. This prevents applications from crashing, but significantly slows down performance as disk access is much slower than RAM. 9.4 Mounting and unmounting, connecting file systems. For a file system on a partition to be accessible, it must be mounted. Mounting is the process of making a file system available at a specific location, a directory within the Linux file system hierarchy. Mount point, the directory where a file system is attached, is called a mount point. For example, /dev/sda2 might be mounted at boot and dev/sda3 at. The mount command, used to manually mount a file system. Sudo mount /dev/sdb1 mnt/data. This mounts the first partition of the second disk to the /mnt/data directory. The umount command, used to detach an already mounted file system. You must specify either the device or the mount point. Sudo umount mnt/data or sudo umount dev/sdb1. Important. You cannot umount a file system if it's currently in use, e.g., a user has a CD session inside it or a program is accessing files on it. You'll get an error like target is busy. You might need to use lsoff, list open files, or fuser to find out what processes are using the mount point. 9.4.1 Persistent mounts, the /etc/fstab file. To ensure file systems are mounted automatically every time the system boots, their information is stored in the etc/fstab file system table file. This file describes the required mounts, their location, file system type, and options. Example entry in etc/fstab. UUID equals abt 1234f5678, data ext4 defaults 02. UUID equals the universal unique identifier of the partition. Using UUIDs is best practice as device names /dev/sdb1 can change if disks are added or removed. Data, the mount point directory where it will be attached. ext4, the file system type. Defaults, common mounting options RW, Suede, Dev, Exec, Auto, Nouser, Async. 0. Dump field usually 0, related to backup utilities. 2. Pass number order of FSCK checks at boot, 0 to skip, 1 for root, 2 for others. After editing etc/fstab, you can test it without rebooting by simply running sudo mount a mount all. This command attempts to mount all specified file systems that are not already mounted. If there are errors in your fstab, your system might fail to boot. Always back up fstab before editing it. 9.5 Checking disk space and usage. Two commands are essential for monitoring disk space. df disk free. Summarize disk usage of file systems. The df command reports the amount of disk space used and available on currently mounted file systems. dfh. H displays sizes in human-readable format, e.g., 1K 234M 2G. Example output. File system, size used avail use % mounted on TMPFS 389M, 1.1M 388M, 1% run. Dev/SDA 319G, 5.2G 13G 29%. Dev/SDA 2 1014M 246, M 769M, 25% boot. TMPFS 389, M0 389, M0% dev/SHM. This shows how much space is used, available, and percentage used for each mounted file system. Do disk usage, estimate file space usage. While df shows overall file system usage, do shows the disk space used by specific files or directories. This is useful for finding out what is consuming disk space within a particular directory. Do sh var/log. S summarize total for each argument. H human readable format. This will show you the total size of the /var/log directory. To find the largest directories within your current location, sudo do h max depth equals 1. Sort rh. Max depth equals 1. Limits the scan to one directory level deep. Sort rh sorts the output in reverse numerical order, making the largest directories appear first. Requires sudo to access all files. 9.6 Managing storage. Practical tools. 9.6.1 Partitioning tools. Parted and fdisk. Parted, a powerful and modern partitioning tool that supports both MBR and GPT partition tables, and can be used on disks larger than 2 TB. It can also resize partitions. Interactive mode. Sudo parted dev/sdb replaced sdb with the disk you want to partition. Parted print shows current partition table. Parted mclabel GPT creates a new GPT partition table. Parted mkpart primary ext4 1 MB 50% creates a primary partition type ext4 from 1 MB to 50% of the disk. Parted quit exits. Parted can also be used non-interactively for scripting. Fdisk, an older command line utility primarily used for MBR partition tables. It's interactive and relatively simple for basic MBR partitioning. Interactive mode. Sudo fdisk dev/sdb. M print the help menu. P print the current partition table. N create a new partition. D delete a partition. W write changes to disk and exit. Q quit without saving changes. Important note on partitioning. Partitioning a disk will irrevocably erase data if you create new partition tables or modify existing partitions. Always back up your data before performing any partitioning operations, especially on physical machines. Practice extensively in your virtual machine lab first. 9.6.2 Creating file systems. MKFS. Once a partition is created, you must format it with a file system before you can use it. The mkfs command, make file system, is used for this. Format with ext4. Sudo mkfs ext4 dev/sdb1. Format with xfs. Sudo mkfs xfs dev/sdb1. Creating a swap partition from a partition. Sudo mkswap dev/sdb2. Sudo swapon/dev/sdb2 to activate it immediately. Remember to add swap partitions to etc/fstab as well using their UUID. 9.7 Resizing file systems. Resizing partitions and their file systems can be complex and risky, specifically when shrinking. Extending is generally safer. Resize to FS. Used to resize X2, X3, or X4 file systems. To expand to fill the available partition space after enlarging the partition with parted. Sudo resize to fs/dev/sda3. To shrink requires careful calculation and often unmounting. Sudo resize to fs dev/sda3 10G shrinks to 10 GB. The underlying partition must then be shrunk to match or be slightly larger. Other file systems like XFS and BTRFS have their own resizing tools, e.g., XFS growths for XFS, BTRFS file system resize for BTRFS. 9.8 Troubleshooting storage issues. No space left on device. This commonly feared error means a file system is full. Use df-h to identify which file system is full. Use do-sh in various directories, starting from the root of the full file system, to pinpoint the large files or directories consuming space step by step. Common culprits: var/log large log files, /tmp temporary files, /var/www website content, backups, user home directories. Delete unnecessary files after careful consideration and backup. Consider increasing the partition size if space is available on the disk, or adding a new disk. File system not mounting on boot. Check etc/fstab for typos, punctuation, device name UUID mount point options. Use sudo mount a to test. Corrupted file system. If a system crashes or experiences sudden power loss, a file system can become corrupted. Unmount the file system if possible. Use fsck file system check. Sudo fsck fvdev/sda3 replace sda3 with the relevant partition. This tool attempts to repair file system inconsistencies. Caution: running fsck on a mounted file system can cause further corruption. Do not run it on the root file system while the system is running using fsck directly. The system's boot process usually runs fsck automatically if needed for the root partition. Managing storage is a hands-on skill. The best way to learn is to add a new virtual hard disk to your VM, then practice partitioning, formatting, mounting, and filling it with dummy data. Summary and key takeaways. Linux identifies storage devices as block devices, e.g., /dev/sda, /dev/nvme0n1, and their partitions, e.g., /dev/sda1. Use lsblk to view. Partitions logically divide a physical disk. MBR is older, limited-size partitions. GPT is modern, large disks, many partitions. A file system organizes data on a partition. ext4 is standard, XFS for large files, BTRFS for advanced features. Swap provides virtual memory. A file system must be mounted at a directory, mount point to be accessible. Use sudo mount and sudo umount. etc/fstab ensures file systems are mounted automatically at boot using device UIDs. Check disk space with df-h file system wide and do-h directory file specific. Partitioning tools: parted modern, mclabel, mkpart, print, and fdisk mbr specific. Formatting tools: mkfs ext4, mkfs xfs, mkswap. Resizing tools: resize to fs for ext4. Troubleshooting: no space left on device. Use df, do, unmounted file systems, /etc/fstab errors, corrupted file systems, fsck. Always backup data before modifying partitions or file systems. Practice in a VM. Practical exercise: add a new virtual disk to your VM. Power off your Ubuntu VM in VirtualBox. Go to VM Settings Storage. Under the controller, SATA section, click the green plus icon to add hard disk. Choose Create New Disk, and accept the defaults VDI dynamically allocated. Give it a size e.g. 5 to 10 GB. Start your VM. Identify and partition the new disk. Run lsblk. You should now see a new disk, likely SDB, with no partitions. Launch parted on your new disk. Sudo parted dev/sdb. Inside parted, mclabel GPT creates a GPT partition table. mkpart primary ext4 0%, 100%. Creates a single primary partition using 100% of the disk. Print, verify the new partition SDB1. Quit, write changes, and exit. Run lsblk again to confirm SDB1 now exists. Format and mount the new partition. Format the new partition with ext4. Sudo mkfs ext4 dev/sdb1. Create a mount point. Sudo mkdir/mnt/new data. Mount the partition. Sudo mount/dev/sdb 1 mnt/new data. Run df-h and confirm /mnt/new data is mounted and has space. Make mount persistent. Get the UUID of the new partition. Sudo blkid dev/sdb1. Copy the UUID. Open etc/fstab for editing. Sudo nano etc/fstab. Add a new line at the end using the UUID. UUID equals yourstb. 1 UUID mnt /new data ext4 defaults 02. Save and exit nano. Unmount the partition. Sudo umount mnt/new data. Test the fstab entry. Sudo mount a. Run df-h again to confirm it mounted successfully. Cleanup optional for next chapter. If you want to remove the new disk entirely, you'd typically unmount it, remove its etc/fstab entry, power off the VM, and remove the virtual hard disk from VirtualBox settings. Further reading resources: man lsblk, man parted, man fdisk, man mkfs, man mount, man umount, man df, man do, man fsck for detailed command usage. Arch Linux Wiki. File systems, excellent resource for various file system types. Official documentation for ext4, XFS, and BTRFS. Chapter 10. System Monitoring and Logging. Keeping an eye on things. As a Linux system administrator, your work is never truly done once a system is set up. Like a ship captain constantly checking their instruments, you must continuously monitor your servers to ensure they are performing optimally, are free from errors, and are not under attack. This chapter delves into the vital practices of system monitoring and logging, providing you with the tools and techniques to keep a vigilant eye on your Linux systems, diagnose problems, and react proactively. 10.1. The importance of monitoring and logging. Imagine a critical production server suddenly slowing down, or, worse, becoming unresponsive. Without proper monitoring and logging, diagnosing the root cause would be like searching for a needle in a haystack in the dark. Monitoring, the active process of collecting and analyzing data about your system's performance and health. This includes metrics like CPU usage, memory consumption, disk I/O, network traffic, and running processes. Proactive problem detection. Identify bottlenecks or unusual behavior before they lead to outages. Performance optimization. Understand system workload and resource usage to optimize configurations or plan upgrades. Capacity planning. Gather historical data to predict future resource needs. Security insight. Detect unusual activity that might indicate a security breach. Logging. The passive, continuous recording of events and messages generated by the operating system, applications, and services. Post-mortem analysis. Provides a detailed history for diagnosing past issues. Security auditing. Records login attempts, sudo usage, and other security-relevant events. Compliance. Many regulatory requirements demand robust logging. Application debugging. Developers use application logs to find and fix software bugs. 10.2 Core Monitoring Metrics. Monitoring focuses on key performance indicators, KPIs of your system resources. CPU usage, how busy your processor is. Look for high utilization, especially if it's system or I/O wait time, which can indicate bottlenecks outside the CPU itself. Memory usage, how much RAM is being used versus available. Look for high swap usage, which indicates memory pressure and degraded performance. Disk I/O, how actively your storage devices are reading and writing data. High disk I/O can indicate disk-bound applications or a slow storage system. Network I/O, the amount of data being transmitted and received over the network interfaces. High network usage can point to heavy traffic, DDoS attacks, or misconfigured services. Load average. A common Linux metric indicating the average number of processes in the run queue, waiting for CPU time, or uninterruptible sleep state, waiting for I/O over the last one, 5 and 15 minutes. A general rule of thumb for single-core systems is that a load average above 1.0 indicates your CPU is overloaded. For multi-core systems, divide the load average by the number of CPU cores. 10.3 Basic Real-Time Monitoring Tools. Quick review. We've already touched upon these in Chapter 6, Processes and Services, but they are your first line of defense for real-time problem identification. Top. displays a dynamic, real-time view of running processes sorted by CPU usage. Great for a quick overview of what's consuming resources. Type top, then Q to quit. HTOP, an enhanced, interactive version of top with a more user-friendly interface. Highly recommended for its visual clarity. Install, sudo apt install htop or sudo dnf install htop. Type htop, then F10 or Q to quit. 10.4 Historical periodic monitoring tools. For deeper analysis or to collect data over time, you need tools that provide historical snapshots or aggregate statistics. These tools are often part of the systat package. Install systat, ubuntu/debian, sudo apt install systat. CentOS Red Hat, sudo dnf install systat. SAR, System Activity Reporter. SAR is a powerful command line utility for collecting, reporting, and saving system activity information. It can show historical data or real-time data for various metrics. CPU usage. SAR U53 reports CPU usage every 5 seconds 3 times. Memory usage, SAR R53. Disk I/O, SAR B53. Network I/O, SAR NDV53. Load average, SAR Q53. SAR data is typically collected by a system service and stored in binary files e.g. /var/log/systat/SA-Roman20, where XX is the day of the month. You can report on past days. SAR UFVAR/log/systat/SA15 for reports of the 15th of the month. VMstat, Virtual Memory Statistics, reports on processes, memory, paging, block I/O, traps, and CPU activity. It gives you a quick snapshot of system performance every second. VMstat15 reports every 1 second 5 times. Look at R, processes waiting for runtime, and B, processes in uninterruptible sleep. CISO swap-in, swap-out indicate memory pressure. IOStat, CPU disk I/O statistics, reports on CPU utilization, and I/O statistics for devices, partitions, and network file systems. Useful for identifying disk bottlenecks. IOStat XDM25, extended statistics, device utilization, megabytes, every 2 seconds 5 times. Look at %util, percentage of time the device was busy, and a wait, average wait time for I/O requests. High values indicate disk I/O bottlenecks. 10.5 Logging systems. Linux systems generate a vast amount of log data, which is captured and managed by logging services. 10.5.1 Traditional syslog, rsyslog, syslog-ng. Historically, most Linux distributions use the syslog protocol. Modern implementations like rsyslog or syslog-ng are installed by default and manage the collection, filtering, and routing of log messages. Log locations. Syslog messages are typically stored in plain text files in the /var/log/ directory. Common log files in var/log/, var/log/syslog, debian/ubuntu, or var/log/messages, CentOS Red Hat. General system activity, boot messages, non-kernel issues. var/log/auth-log, debian/ubuntu, or var/log/secure, CentOS Red Hat. All authentication-related messages, login attempts, sudo usage, critical for security auditing. var/log/kernlog, kernel messages, often related to hardware issues or kernel modules. var/log/dmesk, kernel ring buffer messages from boot and startup. var/log/apt/historylog, debian/ubuntu, history of package installations and removals. var/log/bootlog, messages logged during system boot. Dedicated application log files, e.g., /var/log/auth-log for web servers like Apache/Nginx, /var/log/mysql/ for MySQL MariaDB. Reading log files. Cat var/log/syslog displays the entire file may be very long. Less var/log/auth-log for larger files allows scrolling, space for page down, B for page up, Q to quit. Tail f var/log/syslog follows the log file in real time, showing new entries as they are written. Essential for watching live activity. Press Ctrl+C to quit. grep failed password var/log/auth-log filters log entries for specific keywords for security auditing. 10.5.2 System Journal journaled. Modern Linux distributions using systemed, like Ubuntu, CentOS, Fedora, often use journaled as their primary logging system. The journal collects log data from various sources, kernel, applications, services, and stores it in a structured, often binary format. Advantages of journaled. Centralized, all logs are in one place. Structured, easier to query and filter. Metadata, records additional information, PID, UID, systemed unit. Integrity, can be configured for authenticated logging to detect tampering. The journoctl command. This is the tool to query and view the journal. Journoctl displays all system logs, can be massive. Journoctl F follows the journal in real time like tail F. Journoctl Z shows recent log entries, X provides context explanation, E jumps to end. Journoctl U SSHD shows logs specifically for the SSH daemon. Journoctl PR shows only errors, warnings, or other specific priority levels. Journoctl since 2023 to 4 to 110.00 until 2023 to 4 to 111.00. Filter by time ranges. Journoctl K shows only kernel messages. Journoctl disk usage shows how much disk space the journal uses. Persistence. By default, the journal might be stored in RAM and cleared on reboot, non-persistent. To make it persistent, log files stored on disk, you need to create the directory var/log/journal. Sudo mkdir p var/log/journal. Sudo systemctl restart, system journaled. The directory must be created before the service starts. 10.6 Log rotation, log rotate. Log files can grow very large, consuming significant disk space and making them difficult to manage. Log rotation is the process of archiving, compressing, and deleting old log files periodically. Logrotate tool, the logrotate utility handles this automatically. It's usually installed by default and runs daily via a cron job. Configuration files, etc/logrotate.conf. The main configuration file containing global defaults, etc/logrotate_d/. This directory contains individual configuration files for specific applications or services. When a package is installed, e.g. Apache Nginx, it often places its logrotate configuration here. Example logrotate entry from /etc/logrotate_d/nginx. var/log/nginx/log. Daily. Missingok. Rotate 14. Compress. Delay compress. Node Effici. Create 640 www data atom. Shared scripts. Prorotate. If d/etc/logrotate d/httpd prorotate. Then backslash. Run part /etc/logrotate d/httpd prorotate. Backslash. Phi backslash. End script. Post rotate. Invoker cd. nginx rotate dev/null2 and 1. End script. Daily. Rotate logs daily. Rotate 14. Keep 14 rotated log files. Compress old log files. Missingok, don't report an error if the log file is missing. Node empty, don't rotate if the log file is empty. Create 640 www data atom. Create new log file with permissions 640 owned by www data atom. Post rotate. And script. Commands to run after rotation, e.g., tell nginx to reload its logs. To manually force a rotation for a configured log file, sudo logrotate f/etc/logrotate d/nginx. Logrotate d/etc/logrotate d/nginx. Debug mode shows what it would do without actually doing it. 10.7 Practical applications and troubleshooting with monitoring and logging. Diagnosing high load average. Check top/htop. Identify top CPU memory consumers. Check vmstat. High R run Q indicates CPU contention. High CISO indicates memory pressure. High BIBO block and out can indicate disk I/O issues. Check IOStat. High %util for disks suggests disk bottleneck. Check SAR. Look for historical trends. Debugging application issues. Check application-specific logs, e.g., /var/log/apache2/error log. Check journoctl U service name for the application's systemed unit. Check syslog/messages for system-level errors related to the application. Investigating security incidents. Check var/log/authlog or sudo journoctl u ssshdg failed password for unusual login attempts. Look for unexpected sudo commands or user activity. Check application logs for signs of compromise, e.g., unusual web requests. Disk space management, df/h to find full partitions. Do sh and sort rh to find large directories within those partitions. Ensure logrotate is correctly configured for very large log files. Mastering monitoring and logging transforms you from a reactive fixer to a proactive manager. By continuously observing your systems and knowing where to look in the logs, you'll be able to identify and resolve issues much more quickly, and often prevent them from becoming critical incidents. Summary and key takeaways. Monitoring, proactive, real-time historical and logging, passive, event recording, are critical for system health, performance, security, and troubleshooting. Key monitoring metrics: CPU, memory, disk I/O, network I/O, load average. Real-time monitoring tools, top, htop. Historical periodic monitoring tools, systet package, SAR. System activity reporter, CPU, memory, disk, network load. VMstat, virtual memory statistics. IOStat, disk I/O statistics. Logging systems, syslog, e.g., rsyslogd. Traditional, stores logs in plain text files under /var/log/. Syslog, authlog, kernlog, application-specific logs. Read with cat less tail f grep. System journal journaled. Modern on-system systems, stores structured, often binary, logs. Query with journoctl, e.g., journoctl u service name, journoctl f, journoctl p earth. Set persistence with sudo mkdir var/log/journal. Log rotation, logrotate. Automates archiving, compressing, and deleting old log files to manage disk space. Configured in /etc/logrotate.conf and /etc/logrotated/. Troubleshooting flow. Use top/htop for quick identification, then vmstat/iostat/sar for deeper performance analysis, and finally journoctl/log files for root cause analysis of errors or warnings. Practical exercise. System load and metrics monitoring. If not already, install systat. Sudo apt install systat or sudo dnf install systat. Run top and note the load average and CPU memory statistics. Run htop and visually inspect CPU and memory usage. Run sar u15 CPU, then sar r15 memory, then sar q15 load average. Observe the data. Generate some activity. In another terminal, run while true, do echo, stress test. Done or even dd if =/dev/0 of testfile bs =1m count =1000. Watch how your CPU disk usage spikes in top and SAR or iostat. Remember Ctrl+C to stop the stress test. Inspect iostat xdm15. Pay attention to %util for your main disk. Exploring logs, logging, view your boot log messages, dmesc less. See general system messages, less var/log/syslog, Ubuntu, or less var/log/messages, CentOS. Search for error. Check authentication logs, less var/log/authlog, Ubuntu, or less var/log/secure, CentOS. Search for your own username or accepted password. Simulate activity. Open a new terminal and try a few incorrect sudo commands, e.g., sudo zis. Then, in your main terminal, run tail fvar/log/authlog. See if you can spot your failed sudo attempts. Now use journoctl if on systemd, journoctl f, watch live logs, journoctl z, see recent events with explanations, journoctl p warning, see only warnings and higher, journoctl u sshd, see only ssh daemon logs. Try to start-stop the SSH service and watch journoctl u ssshdf. Log rotation. Inspect your logrotate configuration. cat etc/logrotate.conf and ls etc/logrotate_d/. Find a small log file, e.g., if =/dev/0 of =/var/log/myloglog bs =1m count =1, then echo test var/log/myloglog. Create a simple logrotate config for it in slash etc slash logrotate d slash var slash log slash myloglog. Size 1K. Rotate 1. Compress. Missingok. Note fmt. Force a rotation. Sudo logrotate f slash etc slash logrotate d slash mylog. Check var slash log slash for myloglog and myloglog.1. GZ. Further reading resources. Man sar, man vmstat, man iostat, man dmesc, man journoctal, man logrotate for detailed command options. System documentation, specifically system journaled. Distro-specific logging guides, e.g. for rsyslog configuration. Online resources for Linux performance tuning. Chapter 11, Basic Security Hardening. Protecting your Linux box. When managing a Linux system, security isn't just a feature, it's a fundamental responsibility. Especially for servers connected to the internet, simply installing Linux isn't enough. Your system is a target. This chapter introduces essential concepts and practical steps for basic security hardening, making your Linux server resilient against common threats and vulnerabilities. While enterprise-level security is a vast and specialized field, these foundational practices will significantly improve your system's posture. 11.1. The importance of security hardening. Why prioritize hardening? The internet is a hostile environment. Automated bots continuously scan for vulnerable systems, attempting brute force attacks, exploiting known weaknesses, and launching malware. A single compromised server can lead to data breaches, service disruption, and reputational damage. Security hardening is about reducing the attack surface, the points where an attacker can try to gain unauthorized access, and increasing the resilience, the ability to withstand or recover from attacks of your system. 11.2. Core Security Principles. Several principles guide effective security practices. Principle of least privilege. Grant users and services only the minimum necessary permissions to perform their functions. Reviewed in Chapter 5. Defense in depth. Employ multiple layers of security controls, so if one fails, others can still protect the system. Regular updates. Keep all software, OS, applications, kernel, up to date to patch known vulnerabilities. Reviewed in Chapter 8. Audit and monitor. Regularly review logs for suspicious activity and monitor system behavior. Reviewed in Chapter 10. Backup and recovery. Have a plan to restore your data and systems in case of compromise or failure. 11.3. Initial system setup security best practices. Many security measures should be considered from the very beginning of a server's life. 11.3.1. Strong passwords and passphrases. This is the simplest, yet most effective first line of defense. Complexity. Use a mix of uppercase and lowercase letters, numbers, and symbols. Length. Longer passwords are harder to crack. Aim for at least 12 to 16 characters. Uniqueness. Never reuse passwords across different systems or services. Passphrases. Consider using passphrases, multiple words, or a sentence, which are longer and easier to remember, yet more difficult to guess. 11.3.2. Non-root user for daily tasks. Never log in directly as root for routine administrative tasks. Log in with a standard user account that has sudo privileges. Use sudo only when root privileges are absolutely necessary. This limits the blast radius if your primary user account is compromised. On fresh installations, some cloud providers disable direct root login by default, which is a good security practice. 11.3.3. Remove unused software and services. Every piece of software installed and every service running represents a potential vulnerability. Uninstall unnecessary packages. Use sudo apt-purge package name or sudo dnf remove package name. Disable unnecessary services. Use sudo systemctl disable service name and sudo systemctl stop service name. Review what services are running, systemctl list unit files type equals service, and only enable those you explicitly need. 11.4. Securing SSH, the administrator's gateway. SSH is your primary remote access tool. Securing it is paramount. 11.4.1 Chain, default SSH port optional but recommended. By default, SSH listens on port 22. Attackers know this and constantly scan port 22 for brute force attacks. Changing the port makes your server less visible to automated scans. Edit the SSH daemon configuration file. Sudo nano etc /ssh deconfig. Find the line hash port 22. Uncomment it, remove, and change 22 to a high unused port number, e.g., 2222, 22022. Restart SSH. Sudo systematically restart SSHD. Important, remember to update your firewall rules, Chapter 7, to allow traffic on the new SSH port and remove the rule for port 22. If you forget, you'll be locked out. When connecting, you'll need to specify the new port, SSH P2222 username at your server rep. 11.4.2 Disable password authentication, mandatory for production. Instead of passwords, use SSH key-based authentication. This is much more secure. You generate a pair of keys, a private key, kept secret on your local machine, and a public key placed on the server. When you connect, your local SSH client presents the public key to the server. The server can cryptographically verify it without ever transmitting your private key or password. Steps to implement SSH key authentication. Generate SSH keys on your local machine. SSH keygen, TRSA, B4096C, your email at example.com. TRSA specifies the RSA algorithm, B4096, sets the key length to 4096 bits, stronger. C adds a comment to identify the key. It will prompt for a passphrase. Use a strong passphrase for your private key. This encrypts the private key, adding another layer of security in case your private key is ever stolen. This generates two files by default in /SSH/ on your local machine. IDSA private key and IDSA pub public key. Copy the public key to your Linux server. SSH copy ID /SSH/IDSA pub username at your server rep. This command copies your public key to the server's /SSH/authorized keys file. It will typically prompt for your password once to connect. Disable password authentication on the server. Edit sudo nano etc /SSH/SSH deconfig on the server. Find and change. Password authentication no. Ensure permaroot login no is also set. Restart SSH. Sudo systematically restart SSHD. Before logging out, open a new terminal or SSH session and try to connect using your SSH key. If it fails, re-enable password authentication and troubleshoot. Do not proceed until you can successfully log in with your SSH key. 11.4.3 Fail to ban, automated brute force protection. Fail to ban is a service that scans log files, like authlog, for suspicious activity, e.g., repeated failed SSH login attempts, and automatically bans the offending IP addresses using firewall rules for a set period. Install fail to ban, Ubuntu/Debian, sudo apt install fail to ban. CentOS Red Hat, sudo dnf install fail to ban. Configure fail to ban. The main configuration is in etc failtobanjail.conf. Never edit this file directly. System updates might overwrite it. Instead, create a local override file. Sudo nano etc failtobanjail local. Add content like this for SSH, default. Hash ban hosts for 1 hour. Ban time equals 3600. Hash don't ban loopback addresses, etc. Ignore ape equals 127.0.0.1/8. 1. SSHD. Enabled equals true. Port equals SSH. SFTP hash or your custom SSH port. Log path equals %, log s. Max retrieve equals 3 hash, how many failures before a ban. Find time equals 600 hash time window for max retrieve, 10 minutes. Save and exit. Restart fail to ban. Sudo systematically restart fail to ban. Check status, sudo fail to ban client status SSHD. You can also see active bans. 11.5 Firewall, recap from Chapter 7. A properly configured firewall is your system's primary barrier against unwanted network access. Allow only the minimum necessary incoming ports. Deny everything else by default. UFW Ubuntu/Debian. Sudo ufwa default deny incoming, then sudo ufwa allow SSH and other services. Firewalled CentOS Red Hat. Sudo firewall cmd set default zone equals public, then sudo firewall cmd add service equals SSH permanent and other services. 11.6 System updates. Recap from Chapter 8. Maintaining an up-to-date system is continuous security hardening. Regularly apply updates to the OS, kernel, and all installed software. Many exploits target known vulnerabilities in outdated software. Ubuntu/Debian, sudo apt update and an sudo apt upgrade. CentOS Red Hat, sudo DNF update. Consider enabling unattended upgrades for security patches, but always monitor the process. 11.7 File integrity monitoring, basic check. Tools like AID, Advanced Intrusion Detection Environment, can periodically scan your system files and compare them against a baseline database. If any critical system files are modified, e.g., /bin/ls/usr/bin/sudo, it generates an alert. This helps detect rootkits or unauthorized modifications. Install AID. Ubuntu/Debian, sudo apt install AID common. CentOS Red Hat, sudo DNF install AID. Initialize database first time, sudo AID init. This generates the baseline. Rename AIDDBNew to AIDDB. Sudo mv/var/lib/aid/aidbnu/var/lib/aid/aidDB. Run a check later. Sudo aid check. You'd typically schedule this to run periodically via cron and review the output. 11.8 Audit and logging. Recap from Chapter 10. Review your logs regularly, especially authentication logs, /var/log/authlog or journoctal USSHD, journoctal PR. For unusual login attempts, sudo usage, or application errors that might indicate an attack or compromise. 11.9 Limiting the root account. While sudo is preferred, there are other ways to limit root access. Disable direct root login via SSH. Ensure permatroot login no is set in etc/ssh/sshDconfig. Remove root password. While generally not recommended for new multi-purpose servers, sudo passwd droot can remove the root password, forcing all root access through sudo. You then rely solely on sudo for administrative tasks, which is the preferred method anyway. However, this could complicate recovery if the sudo configuration or specific users are somehow broken. 11.1 Zero malware and virus scanners. While less prevalent than on Windows, Linux systems can still be affected by malware. ClamAV, a popular open-source antivirus engine. Install. Sudo apt install clamofdaemon or sudo DNF. Install clamov update. Update virus definitions. Sudo freshclam. Scan a directory. Clamscan rbel ihome. 11.1 1. Secure configuration files and directories. Permissions. Ensure critical configuration files and executables have appropriate permissions. Chapter 4. Configuration files that contain sensitive data, e.g., database passwords, API keys, should only be readable by the user group that legitimately needs access. Generally, 600 or 640 for files, and 700 or 750 for directories are good starting points. Critical executables should typically be owned by root and only executable by necessary users. 755 or even 700 if only root runs them. Final reminder: no system is 100% secure. Security is an ongoing process, not a one-time setup. It requires continuous vigilance, learning, and adaptation to new threats. These basic steps provide a strong foundation for protecting your Linux systems. Summary and key takeaways. Security hardening is crucial for protecting Linux systems from common threats by reducing attack surface and increasing resilience. Core principles: least privilege, defense in depth, regular updates, audit monitor, backup. Initial setup: use strong, unique passwords, passphrases. Operate as a non-root user with sudo. Remove unnecessary software services. SSH security: change default port optional, but good first line of defense. Use SSH key-based authentication and disable password authentication. Password authentication no, permatroot login no in etc/ssh/sshDconfig. Implement fail-to-ban to automatically ban brute force attackers. Firewall: always enable and configure a firewall, UFW or firewalled, to allow only necessary incoming traffic, e.g., SSH, HTTP. System updates: crucial for patching vulnerabilities, apt upgrade, DNF update. File integrity monitoring, AID. Establish a baseline and regularly check for unauthorized changes to critical system files. Audit and logging. Continuously review logs for suspicious activity. Account protection. Disable direct root login via SSH. Malware scanners. Use tools like ClamAV for occasional scanning. Secure permissions. Ensure critical configuration files and directories have restrictive permissions. Practical exercise. Strengthen SSH. Change SSH port. Edit etc/SSH/SSH deconfig. Change port 22 to 2222 or similar. Remember your firewall rules. Allow 2222, delete 22. Restart SSHD. Test from a new terminal. Generate SSH keys on your local machine. If you haven't already, run SSH keygen TRSA B4096. Use a passphrase. Copy public key to server. SSH copy ID I tilde/. SSH/idasapub your username at your server IP. P2222, use your new port. Disable password auth. Edit etc/SSH/SSH deconfig again. Set password authentication no and permatroot login no. Restart SSHD. Test logging in with your key before disconnecting your current session. Install and configure fail2ban. Follow installation steps. Create etc. fail2ban jail local and add the SSHD section. Restart fail2ban. Check its status, fail2ban client status SSHD. Try intentionally failing SSH logins from another IP if possible, or wait for bans to see it in action. Cleanup. List running services. System.tl list unit files type equals service. Identify any services you absolutely don't need, e.g., cups if it's a server, mode manager, whoopsie. Disable and stop them. Sudo system.tl disable service name and sudo system.tl stop service name. Remove software you didn't intend to keep, e.g., Nginx or HTTPD if you installed it purely for testing earlier. Sudo apt purge Nginx or sudo DNF remove HTTPD. Run sudo apt auto remove or sudo DNF auto remove. Basic file integrity check AID. Install AID. Initialize the database. Sudo AID init. Create a test file for AID to detect. Echo malicious data. Sudo tbin/testmalwareful. Run a check. Sudo AID check. Observe the reported change. Clean up the test file. Sudo rm/bin/testmalwareful. You would typically reinitialize the baseline sudo mv/var/lib/aid/var/lib/aid/aiddb after legitimate system changes. Then run sudo aid check again. Further reading resources. Man SSH deconfig, Man SSH keygen, Man SSH copy ID, Man fail2ban. CIS, Center for Internet Security, benchmarks for Linux, provide detailed hardening configurations. OWASP, Open Web Application Security Project, resources. NIST, National Institute of Standards and Technology, Cybersecurity Guidelines. Official documentation for your distribution's security guides. Chapter 12. Automation with Shell Scripting, making Linux work for you. So far, you've learned how to interact with your Linux system by typing commands one by one. But what if you need to perform a sequence of commands repeatedly, perhaps daily, weekly, or after certain events? Typing them manually is inefficient, prone to errors, and scales poorly. This is where automation with shell scripting comes in. Shell scripting is one of the most powerful tools in a Linux administrator's arsenal, allowing you to streamline routine tasks, enforce consistency, and free up valuable time. 12.1 The Power of Automation. Why should you learn to script? Efficiency. Automate repetitive tasks that would otherwise consume a lot of your time. Think about daily backup routines, log cleanups, or system health checks. Consistency. Scripts ensure that a task is performed exactly the same way every time, reducing human error. Speed. Tasks defined in a script execute much faster than if typed manually by an administrator. Scalability. Once a script is written, it can be easily deployed and executed across multiple servers. Problem prevention. Many scripts are designed to monitor systems and take corrective actions proactively, preventing minor issues from escalating into major problems. Documentation. A well-written script serves as a form of executable documentation for a particular process. A shell script is essentially a text file containing a sequence of shell commands. When you execute the script, the shell reads and executes each command in order, just as if you were typing them yourself. 12.2 Your first shell script. Hello, admin. Let's create a simple script to get started. Create a new file. Open your favorite command line text editor like nano hello sh. Add the script content, bin bash. This is my first shell script. Echo hello, Linux administrator. Echo current date and time. Date. Bin bash. This is called the shebang or hashbang. It must be the very first line of your script. It tells the operating system which interpreter, in this case, bash, should be used to execute the script. Lines starting with, these are comments. The shell ignores them. Use comments to explain what your script does, making it easier for yourself and others to understand later. Echo. This command simply prints text to the standard output, your terminal screen. Date. This is a command that prints the current date and time. Save and exit. In nano, press Ctrl+X, then Y to confirm saving, and then enter. Make the script executable. By default, new files aren't executable. You need to grant execute permission. chmod +x hello sh. Run the script /hello sh. The is important because it tells the shell to look for the script in the current directory. You should see output similar to this. Hello, Linux administrator. Current date and time output from the date command. Congratulations, you've written and executed your first shell script. 12.3 Basic shell scripting elements. Let's explore common elements you'll use in your scripts. 12.3.1 Variables. Variables are used to store data, such as numbers, text strings, or the output of commands. To define a variable name equals value. No spaces around the equal sign. Conventionally, variable names are uppercase. To use a variable, variable. Bin bash. Server name equals mi-production server. Logfile equals /var/log/custom-applog. Adminmail equals admin@example.com. Echo processing data for scrvrname. Echo checking log file, logfile. Echo sending alert to adminmail. 12.3.2 User input read. Scripts can be interactive, prompting the user for input. The read command captures user input into a variable. Bin bash. Echo enter your name. Read username. Echo hello username, welcome to the script. When you run this script, it will pause and wait for you to type something and press enter. 12.3.3 Command substitution. You can assign the output of a command to a variable using $parentheses or backticks. $parentheses are preferred as they can be nested. Bin bash. Current date equals $date plus %y%m%d. Free disk space equals $dfh awk nr equals 2 print $4. Echo today's date is current echo free disk space on root partition frediskspace. Here date plus %y%m%d formats the date, and dfh awk nr equals 2 print $4 extracts the available space from the root partition. 12.3.4 Conditional statements. If else. Conditional statements allow your script to make decisions based on whether a certain condition is true or false. Bin bash. Read p enter a number. Number. If number gt10, then echo the number is greater than 10. If number ec10, then echo the number is exactly 10. Else echo the number is less than 10. Phi test or used for evaluating conditions. Ec equal to ni not equal to. GT greater than, LT less than, G greater than or equal to, L less than or equal to, F file true if file exists and is a regular file, D dir true if dir exists and is a directory, Z string true if string is empty, N string true if string is not empty. 12.3.5 Loops. For while, loops allow you to repeat a block of code multiple times. For loop iterating over a list, hash bin bash. For user in Alice Bob Charlie, do. Echo processing user, hash in a real script, you'd add user creation modification commands here. Done. Hash looping through files in a directory. Echo listing txt files. For file in txt. Do. If f file, then hash check if it's actually a file. echo file. Phi. Done. While looping while a condition is true. Hash bin bash. Count equals 1. While count li5. Do. Echo count is count. Count equals $count plus 1, hash increment count. Sleep 1 hash wait for 1 second. Done. Echo loop finished. 12.3.6 Functions. Functions allow you to group related commands into reusable blocks of code. They help organize complex scripts. Bin bash. Define a function. Greeduser. Echo hello, $1. Hash $1 refers to the first argument passed to the function. Echo, this message, is from the greeduser function. Call the function. Greeduser Alice. Greeduser Bob. When you call greeduser Alice, the $1 inside the function becomes Alice. 12.3.7 Exit codes, return status. Every command in Linux and every script returns an exit code, also known as return status. An exit code of 0 typically means the command succeeded. A non-zero exit code, e.g., 1, 2, 127, indicates an error or failure. You can check the exit code of the last executed command using the special variable. Bin bash. ls/non-existent directory. If any 0, then echo error. Directory not found. Phi. You can also use end and or operators. End executes the next command only if the first succeeds. Executes the next command only if the first fails. mkdir nudir and echo, directory created successfully. rmdir anathern and existentir, echo, failed to remove directory. 12.4 Practical scripting examples. Let's put some of these elements together into practical scenarios. 12.4.1 Basic System Health Check. Bin bash. Script to perform a basic system health check. Checks disk space, memory usage, and running services. Logful equals /var/log/healthcheck $, date plus %y, md, log. Threshold disk usage equals 90 hash %. Echo system health check. Date t a allogefile. Check disk usage. Echo t a allogefile. Echo disk usage t a allogefile. Df ht a allogefile. Root disk usage equals $dfh awk nr equals 2 print $5 set s %. If rootdiskWsag, g, thrshwlddiskWsag. Then, echo critical, root partition is at rootdiskWsag %usage. ta logfile. Else, echo info, root partition usage is rootdiskWsag %. ta logfile. Phi, check memory usage. Echo ta logfile. Echo memory usage, ta logfile. Free ht a logfile. Check running web server, Nginx or Apache. Echo ta logfile. Echo web server status, ta logfile. If systemtool is active, quiet Nginx. Then, echo Nginx is running, ta logfile. If systemtool is active quiet Apache 2, then, echo Apache 2 is running, ta logfile. Else, echo no common web server Nginx/Apache 2 found running, ta logfile. Phi, echo health check complete, ta logfile. ta logfile. This command prints to both the screen and appends the output to the specified log file. awk nr equals 2 print $5 set s %. A small pipeline to extract the percentage of disk usage for the root partition and remove the %sign. Systemtool is active, quiet service name. Checks if a service is active without verbose output. 12.4.2 Simple backup script. Bin bash. Script to perform a simple backup of a directory. Source dir equals /var/www/html hash directory to backup. Backup dir equals /mnt/backup/webdata hash where to store backups. Date format equals $date plus %y %m %d %h %m %s. Backup file equals $backupdir/webdata backup $date format targz. Create backup directory if it doesn't exist. mkdir p backup echo starting backup of sourcdir to backup file. Create a compressed tar archive. tar czvf backup file sourcdir. If a x0, then echo backup successful. Echo backup size. Do sh backup awk print $1. Else, echo backup failed. Exit 1 hash exit with an error code. Fi. Optional. Remove old backups, keep last 7 days. Echo, removing backups older than 7 days. Find backup max depth 1 m time plus 7 name, tar-gz delete. Echo script finished. Tar czvf. Creates C, compresses with gzip z, verbose output v, and archives to a file f. Find, delete. A powerful command to find files matching criteria and delete them directly. mtime plus 7 means modified more than 7 days ago. 12.5 Scheduling scripts with cron. Once you have a useful script, you'll want it to run automatically at specific times. This is done using cron, the time-based job scheduler in Linux. Each user can have their own cron tab, cron table file, which lists the jobs they want to schedule. System-wide cron jobs, e.g., for system maintenance, are often placed in directories like /etc/cron daily, /etc/cron weekly, /etc/cron monthly, or directly in /cron tab. 12.5.1 The cron tab command. Edit your user's cron tab e. This opens your personal cron tab file in a text editor, usually Nano or Vim. List your cron tab entries. Cron tab L. Remove your cron tab entries. Cron tab R, use with caution. 12.5.2 Cron tab syntax. Each line in a cron tab file represents a scheduled job and follows a specific format. Minute hour day of month day of week command to execute. Minute 0 to 59. Hours 0 to 23. Day of month 1 to 31. Month 1 to 12 or Jandek. Day of week 0 to 7, where 0 and 7 are Sunday. Command to execute. The full path to your script or command. Special characters. Wildcard means every, e.g., for minute means every minute. Separator for lists, e.g., 115 for minute means at minute 1 and minute 15. Range, e.g., 9 to 17 for hour means from 9 a.m. to 5 p.m. Slash. Step values, e.g., 15 for minute means every 15 minutes. Examples cron tab entries. Path to my script sh runs every minute. Use with extreme caution. Path to my script sh runs at the beginning of every hour, e.g., 00, 10, etc. 03/path/to/my/daily-backup/sh runs every day at 3 o'clock a.m. 020 path to my weekly report sh runs every Sunday at 2 o'clock a.m. 0 or 7 is Sunday. Path/to/my/check service sh runs every 5 minutes. When scheduling a script with cron, it's generally best to provide the full absolute path to the script to avoid issues with the script's environment not finding commands. Cron jobs also don't have a terminal, so ensure any output you want to see is redirected to a log file within the script itself. 12.6 The administrator's mindset for scripting. Start small. Don't try to automate everything at once. Start with simple, repetitive tasks. Test thoroughly. Always test your scripts in a non-production environment, like your VM, before deploying them to live servers. Add comments. Document your code. Future you and others will thank you. Error handling. Use if statements and check exit codes to handle potential failures gracefully. Logging. Include echo statements or redirect output to a log file so you can see what your script did or didn't do. Set E. Add set E at the top of your script. This tells Bash to exit immediately if any command fails, returns a non-zero exit code. This is crucial for preventing unexpected behavior. Shell scripting gives you immense control over your Linux systems. It transforms you from a reactive keyboard typer to a proactive system architect, designing automated solutions that keep your servers running smoothly and securely. Summary and key takeaways. Automation with shell scripting saves time, increases consistency, reduces errors, and improves scalability for administrative tasks. A shell script is a sequence of commands in a text file, starting with a shebang, bin bash. Basic scripting elements, comments, explain code. Variables store data, myvar equals value, accessed with myvar. User input captured with read. Command substitution, command assigns command output to variables. Conditional statements if elif-else with for checks allow decision-making. Loops for while repeat actions. Functions myfunc. Organize reusable code. Exit codes. Indicate command success 0 or failure non-zero. Scheduling with cron. Cron tab E to edit your user's scheduled jobs. Syntax. Minute hour day of month day of week command to execute. Use special characters / for scheduling patterns. Always use absolute paths for scripts in cron jobs. Best practices for scripting. Start small, test thoroughly, add comments, handle errors, log output, and use set E. Practical exercise. Create a simple system report script. Create a script system report sh that uses echo to print a header like daily system report date, prints the output of uptime, shows load average, prints the output of dfh / root disk usage, prints the output of free h memory usage, prints a footer. Make it executable, run it, and observe the output. Add conditional logic. Modify system report sh to check if free disk space on is less than 20%. If it is, echo a warning message like warning. Low disk space. Hint, use dfh with awk and said to extract the percentage, then if with lt. Schedule the script with cron. Move system report sh to a dedicated script directory, e.g. mkdir / scripts. Edit your cron tab. Cron tab E. Add a line to run your system report sh script every day at 3:00 a.m. Your VM might not be running then, so change to for every minute for testing, but remember to remove it after. Redirect the script's output to a log file within the cron job. Home / sysadmin / scripts / system report sh var / log / my system report log 2 and 1. var / log / my system report log. Appends stdout to the log file. 2 and 1. Redirects stdir error messages to the same place as stdout. Save the cron tab. Wait a minute, if testing every minute, and then cat / var / log / my system report log to see if it ran. Experiment with read and if. Create a script guess number sh that asks the user to guess a number between 1 and 10. Use an if / elif / else structure to tell them if they guessed correctly, too high, or too low. Further reading resources. Man Bash, the ultimate bash reference but very dense. Man cron tab, man cron. Bash scripting tutorials. Numerous excellent resources online. Search for Bash scripting tutorial for beginners. Shell scripting. Expert recipes for Linux, Unix, and OpenVMS by Chris F.A. Johnson, a classic reference. Chapter 13. Troubleshooting common issues. When things go wrong. No matter how carefully you configure a Linux system, things inevitably go wrong. Services crash, networks fail, disks fill up, and users call with problems. As a system administrator, your ability to diagnose and resolve these issues is perhaps your most vital skill. This chapter will equip you with a systematic approach to troubleshooting, reviewing common problems, and providing a framework for finding solutions. 13.1. The troubleshooting mindset. A systematic approach. Troubleshooting can be frustrating, especially under pressure. Adopt a methodical, calm approach to increase your chances of success. Don't panic, take a deep breath. Rushing often leads to more mistakes. Define the problem precisely. What exactly happened? E.g., web server is down is vague. Users cannot access www.example.com since 10:30 a.m., and ping to server works but web page won't load is much better. When did it start? Was anything changed just before the problem appeared? The last change is often the culprit. Who is affected? All users, one user, no one specific. What is the impact? Minor inconvenience, critical outage. Gather information, observe. Before acting, collect data. Check system status indicators, top DFH systemtal status. Review relevant logs, journaltil /var /log /. Ask affected users for details and specific error messages. Isolate the problem, divide and conquer. Break down the system into smaller components, network, OS, application, database. Test each component independently to pinpoint the faulty one. Can you ping the server? Network OK layer 1 to 3. Can you SSH into the server? OS running, basic network services OK. Is the web server service running? Application layer. Is the database accessible? Inter-application layer. Formulate hypotheses. Based on the information, make an educated guess about the cause. I think the web server process crashed. It looks like the firewall is blocking port 80. Test hypotheses, experiment. Change one thing at a time and observe the result. If you suspect the web server crashed, try restarting it. If you suspect a firewall, temporarily disable it, only in a controlled, safe environment for testing, or add a rule to test. Rollback, be prepared to undo any changes if they don't fix the problem or make it worse. Document the solution. Once the problem is resolved, record the problem description, steps taken to diagnose, the root cause, the solution implemented, any preventive measures. This builds your knowledge base and helps others. 13.2 General Diagnostic Tools and Techniques, your troubleshooting toolkit. Many of these commands you've already learned. Here's how they are applied in a troubleshooting context. DMESC displays messages from the kernel ring buffer, crucial for hardware issues, boot problems, or driver errors. DMESC-less, view all kernel messages. DMESC-T grep-I error, filter for timestamped error messages. Journoctal, the primary tool for system journal logs. Journoctal-Z, show most recent logs with context and explanations. Journoctal-ZU service name, filter by service. Journoctal since 2 hours ago, filter by time. Journoctal-F, follow new log entries in real time. var/log/directory, traditional plain text log files. lsl var/log/. See available logs. Tail f var/log/auth-log, live monitor authentication attempts. grep, failed password, var/log/auth-log, search for specific patterns. Systemctl state as service. Check the current state of a service, running, stopped, enabled, disabled, last error. Top/htop, real-time process and resource monitoring. Identify high CPU, memory, or I/O usage. DFH. Check overall disk space utilization on mounted file systems. Do sh directory, check disk usage of a specific directory. Do h max depth equals 1, sort RH to find large subdirectories. IP-A. Display IP addresses and network interface status. Ping host, test basic network connectivity to a host. SSTLN, list listening network sockets, which programs are listening on which ports. Traceroute host. Trace the path to a network host. Dig domain, ens lookup domain, troubleshoot DNS resolution. LSL file/dir, check file directory permissions and ownership. id user. Check a user's UID, GID, and group memberships. 13.3 Common troubleshooting scenarios and solutions. Let's apply the mindset and tools to specific recurring problems. 13.3.1 System won't boot/unresponsive after boot. Symptoms: server doesn't reach login prompt, hangs during boot, or continually reboots. Possible causes: corrupted kernel, bad grub configuration, full root partition, invalid etc/fstab entry, hardware failure. Troubleshooting steps: access console. If physical, connect monitor keyboard. If VM, use the VirtualBox console. If remote, you'll need the provider's console access, e.g. cloud dashboard. Grub menu. If you see the grub menu, try booting a previous kernel version. Recovery mode/single user mode. Select Advanced Options for Ubuntu or similar on your distro from grub, then choose Recovery mode. This boots into a minimalist environment, often as root, allowing basic commands. Check DMESC, look for hardware errors. Check disk space, DFH to see if root partition is full. If so, identify and move delete large files. Check fstab, nano etc/fstab. Look for typos, incorrect device names UUIDs, or non-existent mount points. Comment out suspicious entries with hash and try to reboot. You might need to remount the root file system as writable. Mount O remount, RW. Check file system corruption. fsck dev/sdax. Replace SDAX with the troubled partition, usually SDA1 or SDA2 for boot or SDA3 for. You'll likely need to unmount it first if it's not the root partition, or run it from a rescue system. Live CD rescue system. If the system is severely broken, boot from an Ubuntu Live CD, ISO, or a cloud provider's rescue image. You can then root into your installed system to perform repairs, e.g., reset root password, fix fstab, reinstall grub. Mount your root partition. Sudo mount/dev/sdax/mnt. Mount boot if separate. Sudo mount /dev /sday /mnt/boot. Bind other system directories. Sudo mount bind /dev /mnt/dev. Sudo mount bind proc /mnt/proc. Sudo mount bind /sys mnt/sys. Sudo croot mnt. You are now in your installed system's environment. Perform repairs. Exit from croot, sudo umount r/mnt, then reboot. 13.3.2 Permission denied errors. Symptoms: unable to cd into a directory, access a file, run a script, or a service fails to write to its log file. Possible causes: incorrect file directory permissions or ownership. The user group trying to access doesn't have the required RWX bits. Troubleshooting steps: identify user and group. Who is trying to access? Who am I, id, or ps aux for a services user? Check target permissions, lsl path /to/ fill your directory. Check ownership. Does the user belong to the owner or group? If not, do others have the necessary permissions? Confirm RWX bits. File: need R to read, W to write delete, and W on parent directory, X to execute. Directory: need R to list contents, W to create delete within, X to cd into or access anything inside. Adjust permissions ownership. Use sudo chmod e.g. chmod 644 file.txt, chmod 755 directory. Chown e.g. chown user, group file.txt, chown r user, group directory. Verify parent directory. If permission denied on creating deleting files, check permissions of the parent directory, e.g. lsld parent directory. 13.3.3 Network connectivity issues. Symptoms: cannot connect to the internet, cannot SSH internally, web server not reachable. Possible causes: wrong IP config, firewall blocking, DNS issues, bad default gateway, physical problem. Troubleshooting steps: local check. IP is the network interface up and does it have an IP address in the expected range? IPR is the default gateway correctly defined, default via ping 127.0.0.1, test loopback. Ping your localip, test the interface itself. Ping gateway IP, test connectivity to gateway. External check, IP, ping 8.8.8.8, test internet connectivity by IP address. If this fails but gateway ping works, could be a router upstream issue. DNS check. cat etc /resolve.conf. Are valid DNS servers listed? Dig google.com, lookup google.com, test name resolution. If pinging IP works but domain fails, it's a DNS issue. Firewall, sudo ufwa status verbose, Ubuntu, or sudo firewall cmdlistall, CentOS. Is your firewall running and allowing the necessary ports, e.g., 22 for SSH, 8443 for web? If remote, be careful. Temporarily stop firewall to test if it's the culprit, then re-enable and add rules. Sudo systemctl stop ufwa or sudo systemctl stop firewalled. Listening ports, sudo ss-tuln. Is the service actually listening on the correct IP port? E.g., web server listening on 0.0.0.0:80. Network configuration files. Review etc /netplan/ YAML Ubuntu or nmcli cshow, CentOS for correct settings. Apply changes as needed, sudo netplan apply or sudo nmcli cup. Traceroute destination. Discover where packets stop along the path. 13.3.4 Performance problems, slow system. Symptoms: applications are slow, commands take a long time to execute, system feels sluggish. Possible causes: high CPU usage, low RAM, excessive swapping, high disk I/O, heavy network traffic, runaway processes. Troubleshooting steps: top/htop, your first stop. Load average, is it high? E.g., CPU cores. CPU, which processes consume the most CPU? Memory, is RAM full? Is swap being used heavily? See so in VMstat. Identify runaway process. If a single process is consuming excessive resources, investigate it. Is it legitimate? Misconfigured? If necessary, kill it politely first, kill PID, then forcefully kill -9 PID. VMstat 1. Watch real-time process memory, and I/O look for high R run queue, CISO swap activity, BIBO block I/O. IStat XDM1, specifically for disk I/O. Look at percent util, disk utilization for your main drives. High percent util along with high await times indicates a disk bottleneck. SAR. Use SAR to look at historical data trends if the problem is intermittent or occurred in the past. Network, SAR NDEV or nload/iftop. If installed, to check network traffic if it's suspected. Application logs. Check application-specific logs for errors that might indicate an internal performance issue. 13.3.5 Disk space exhaustion. Symptoms: no space left on device errors, applications failing to write, system instability. Possible causes: log files growing out of control, temporary files not cleaned, large user data, forgotten old backups. Troubleshooting steps: DFH. Identify which mounted partition is full. Do H max depth equals 1 path / full partition sort RH. Navigate into the full partition and find the largest directories step by step. Common culprits: var/log/log files. Check log rotate configuration for application logs. Manually truncate large logs if necessary. Echo large logfa log. /tmp/ temporary files. Many are cleaned on reboot. Some apps might leave large files here. var/www/ or opt. Application data, website content, potentially old application backups. User home directories, home. Large user files. Package caches, sudo apt clean ubuntu or sudo dnf clean all CentOS. Old kernel versions, often removed by system updates but can accumulate. Deleted files still held open. If a large file is deleted but a process still has it open, the space won't be freed until the process is restarted. Use lsoff grep deleted to find them. Clean up unnecessary files safely. Back up anything critical before deleting. Consider adding disk space. If cleanup isn't sufficient, you might need to resize partitions or add a new disk. 13.3.6 Service not starting running. Symptoms: systemtl status service shows inactive, dead, or failed. Application isn't accessible. Possible causes: configuration errors, missing dependencies, port conflicts, incorrect permissions, resource limitations. Troubleshooting steps: check status, systemtl status service name. Look for recent error messages in the output. Check journal, journaltl zu service name. This is usually the most detailed source of error information. Check service-specific logs. Many applications write their own logs, e.g., /var/log/apache2/error log, /var/log/nginx/error log, /var/log/mysql/error log. This might contain more application-level details. Configuration file syntax. Many services have commands to test their config without starting, e.g., nginxt apashectl configdist. Errors here are common. Permissions. Is the service user authorized to read its configuration files or write to its log data directories? LSL the relevant files directories. Port conflicts. Sudo sstoln. Is another service already using the required port? Dependencies. Is a required service, e.g., database for a web app, running? Resource limits. Check memory or CPU if services are crashing during startup. 13.4 Effective research and documentation. Don't be afraid to use external resources. No one knows everything. Search engines. Copy and paste exact error messages into Google, DuckDuckGo, or your preferred search engine. Often, someone else has encountered the same problem. Man pages and help. Review the command's documentation for correct usage or options. Community forums, Stack Overflow. These are invaluable resources where people share problems and solutions. Official documentation. Refer to the official documentation for the specific application or service you're troubleshooting. Document everything. As you resolve issues, make notes for future reference. This builds your expertise and helps your team. Troubleshooting is less about memorizing every possible error and more about developing a patient, logical, and systematic approach. With practice, you'll become adept at swiftly diagnosing and resolving issues, often predicting them before they become critical. Summary and key takeaways. Systematic troubleshooting. Approach problems calmly, define precisely, gather info, isolate, hypothesize, test one change at a time, and document. Core diagnostic tools. dmesk journalctul/var/log/ systemctul status top/htop df/do ip/ping/ss/traceroute dig/ens/lookup lsl id. Common scenarios. Boot issues. Use console, grub options, recovery mode, fstab check, fsck, or croot from a live CD. Permission denied. Verify user group permissions RWX and ownership LSL id. Use chmod and chown. Network issues. Check ipconfig, IPR, connectivity, ping, traceroute, DNS, dig, firewall, and listening ports, SS. Performance. Identify resource hogs with top/htop, vmstat, iostat. Look for high load average, CPU, memory, or disk I/O disk full. Use df, h, and do, h to find large files directories. Clean logs, cache temporary files, or expand storage. Service not starting. Check systemctul status, journalctul u, service-specific logs, config file syntax, permissions, and port conflicts, ss-tone. Effective research. Use search engines, man pages, community forums, and official documentation. Document solutions. Build a knowledge base to save time in the future. Practical exercise. Simulate a full disk and fix it. Run dfh to see your current root disk usage. Create a large dummy file. dd if equals/dev/0 of equals tilde/larger file bs equals 1m count equals 1000. Adjust count based on your free space to get your root partition to near 100% full, but don't fill it completely to avoid system instability. Attempt to create a small file. Touch test.txt. Observe the no space left on device error. Use do sh tilde/larger file to confirm its size. Delete the large file, rm tilde/larger file. Run dfh again to see the space freed up. Run sudo apt clean or sudo dnf clean all to free up package cache space. Break and fix firewall for SSH. Important, do this from the VirtualBox console or have two SSH sessions open. Check your SSH port with ss-tone. If using UFW, sudo ufwa deny SSH. Immediately try to SSH from a new local terminal on your host machine. It should fail. From your existing console/SSH session, sudo ufwa allow SSH. Confirm SSH works again from the new terminal. If using firewalled, sudo firewall cmd remove service equals SSH permanent. Sudo firewall cmd reload. Immediately try to SSH from a new local terminal on your host. It should fail. From your existing console/SSH session, sudo firewall cmd add service equals SSH permanent. Sudo firewall cmd reload. Confirm SSH works again from the new terminal. Diagnose a failed service. Create a dummy failing service. Sudo nano etc. system failing app service. Add the following content. Unit. Description equals my failing application. After equals network target. Service. Exec start equals /bin/false. Restart equals on failure. Install. Wanted by equals multi-user target. Sudo systemctul daemon reload. Sudo systemctul start failing app. Sudo systemctul status failing app. It should show failed. Use journalctul u failing app to see why it failed. It failed because bin false always exits with a non-zero status. Sudo systemctul disable failing app. Sudo rm etc. system failing app service. Sudo systemctul daemon reload. Further reading resources. The Practice of System and Network Administration by Limoncelli, Hogan, and Chalup. A comprehensive resource for real-world sysadmin challenges. Online Linux troubleshooting guides specific to your Linux distribution. Your distribution's official wiki and error repositories. Chapter 14, Beyond the Basics, Advanced Topics and Next Steps. Congratulations! You've reached the final chapter of the Practical Linux Administrator. You've taken the first crucial steps on a rewarding journey, moving from understanding fundamental concepts to hands-on configuration and troubleshooting. You've installed a Linux server, navigated its command line, managed users and permissions, configured networking, installed software, monitored system health, and even delved into the world of automation. These are the bedrock skills upon which effective Linux system administration is built. However, the world of Linux and IT in general is vast and ever-evolving. This chapter serves as a compass, pointing you towards the next exciting areas of study and practice that will elevate your skills from a solid foundation to a truly advanced level. 14.1. The importance of continuous learning. The most important takeaway from this entire book is not any single command or configuration file, but the understanding that system administration is a field of continuous learning. Technologies change rapidly, new tools emerge, and security threats evolve. A successful Linux administrator is inherently curious, adaptable, and committed to never stopping their education. Embrace the challenges, celebrate the successes, and remember that every problem you solve is an opportunity to learn something new. 14.2 Next steps. Expanding your Linux expertise. Here are several key areas and advanced topics that build upon the knowledge you've gained in this book. 14.2.1 Cloud computing and virtualization. You've practiced with VirtualBox, but the real world of servers often lives in the cloud. Cloud providers like Amazon Web Services, AWS, Microsoft Azure, Google Cloud Platform, GCP, and digital transformation providers largely run on Linux. Concepts: understand infrastructure as a service IaaS, platform as a service PaaS, functions as a service FaaS, and software as a service SaaS. Provider-specific tools: learn how to provision, manage, and scale Linux instances using the command line tools and web interfaces of your chosen cloud provider. Familiarize yourself with concepts like virtual private clouds, VPCs, security groups, and identity and access management, IAM, within a cloud context. Virtualization technologies. Explore enterprise-grade hypervisors like VMware Effici, KVM, or Proxmox VE, which are used to build private cloud environments. 14.2.2 Configuration management and infrastructure as code ISC. Manually configuring a single server is manageable. Manually configuring hundreds or thousands of servers is a nightmare. Configuration management tools automate server setup, ensure consistency, and prevent configuration drift. This shift is often referred to as infrastructure as code, ISC. Ansible, a popular open-source agentless automation engine. It uses simple YAML files, called playbooks, to define the desired state of your infrastructure. This is often an excellent first ISC tool to learn. Puppet, Chef, SaltStack. Other powerful configuration management tools, often used in larger enterprise environments, typically requiring agents on managed nodes. Terraform. While not a configuration management tool directly, Terraform is a leading ISC tool for provisioning infrastructure, servers, databases, networks, across various cloud providers from code. It pairs well with configuration management tools like Ansible. 14.2.3 Containers and orchestration, Docker, and Kubernetes. Containers have revolutionized application deployment by packaging applications and their dependencies into lightweight, portable, and self-sufficient units. Docker, the leading containerization platform. Learn how to build using Docker files, run, manage, and orchestrate containers. Container orchestration. For managing large-scale container deployments, you'll need an orchestrator. Kubernetes is the undisputed leader in container orchestration, enabling automated deployment, scaling, and management of containerized applications. Learning Kubernetes is a significant step in modern IT operations. 14.2.4 Advanced networking and security. While we covered the basics, networking and security are deep fields. Networking. Explore advanced routing, VPNs, network namespaces, bonding, and advanced firewall IPtables or NF tables, rules. Security. Delve deeper into security-enhanced Linux, SE Linux, or AppArmor, intrusion detection systems, IDS/IPS, vulnerability scanning, penetration testing basics, and advanced access control. Understand concepts like hardening benchmarks, e.g., CIS benchmarks. 14.2.5 Monitoring and logging, centralized solutions. For multiple servers, you need more than Top and Jernoctil. Centralized logging. Solutions like ElkStack, Elasticsearch, Logstash, Kibana, Splunk, or Graylog aggregate logs from all your servers into a central location for analysis and visualization. Advanced monitoring. Tools like Prometheus and Grafana for metrics collection and visualization, Nagios/Zabbix for comprehensive infrastructure monitoring and alerting. Performance tuning. Learn advanced techniques for optimizing kernel parameters, disk I/O, network performance, and application-specific settings. 14.2.6 Scripting and Programming. You've started with Bash scripting, but consider expanding your programming knowledge. Advanced Bash scripting. Master more complex Bash features, advanced error handling, and robust script design. Python. Python is incredibly popular in system administration for its versatility, ease of learning, and vast libraries for everything from network automation to web development and data analysis. It's often the next logical step after Bash. Perl, Go, Ruby, other languages used for scripting and automation in various contexts. 14.3 Building your skills. Practical paths forward. Knowledge is best solidified through practice and engagement. Personal projects. Set up a dedicated virtual machine or a small cloud instance for a personal project. Try hosting a simple website, setting up a database, or configuring a custom application. Break it, fix it, learn from it. Contribute to open source. Get involved in open source projects. This is a fantastic way to learn from experienced developers, contribute to real-world code bases, and build your resume. Online courses and tutorials. Supplement this book with dedicated courses on specific topics, e.g., Docker, Kubernetes, Ansible, Python, from platforms like Coursera, Udemy, Pluralsight, or free resources like FreeCodeCamp. Certifications. Consider industry certifications, e.g., CompTIA Linux Plus, Red Hat Certified System Administrator, RHCSA, Linux Foundation Certified System Administrator, LFCS. These provide structured learning paths and recognized credentials, but practical experience remains key. Join communities. Engage with the Linux community online, forums, Reddit, Stack Exchange, and locally, meetups. Share your knowledge, ask questions, and learn from others' experiences. The Linux community is incredibly supportive. 14.4 The Administrator's Journey, a continuous adventure. You've learned that Linux is everywhere, powering the internet, the cloud, and countless devices. As a Linux system administrator, you are at the heart of this digital world, responsible for keeping the engines humming. It's a challenging role, but also immensely rewarding. The journey you've started with this book is just the beginning. The skills you've acquired are valuable and will serve as your launchpad into increasingly complex and fascinating domains. Keep learning, keep experimenting, and keep building. The practical Linux administrator is not just someone who knows commands. It's someone who understands systems, solves problems, and consistently strives to improve. You are now well on your way to becoming that administrator. Go forth and administer with confidence. The Linux world awaits.